in Electronics and Instrumentation Engineering in 1991 from SATI Vidisha and ME in Communication Systems from Government Engineering College Jabalpur in 1994. He also visited USA, Italy for international conferences through Microsoft Traveling Grant, UGC Grant as well as DST Grant. He is selected for part PhD as well as postdoc in Canada. He has been coordinator of Center for Remote Sensing and Satellite Technology of SGSITS for nearly 6 years. He has published around 85 research papers, including national, international conferences, and SCI journals. He has developed three laboratories in the department, like Microwave Laboratory, Antenna Fabrication Laboratory, as well as Antenna Test and Measurement Laboratory through MHRD, AICTE, and TechWIP funded research facility. He also received funding for wardrobe project and setup of advanced RF and microwave laboratory. He has one patent granted on miniaturization of microstrip patch antenna. He is a coordinator of the Central India's chapter entitled Antenna Test and Measurement Society, running by ISRO and DRDO experts. He is a chairman of Board of Studies as well as Department Quality.
Ma'am, voice is not coming. Your voice is not coming. Are you getting my voice? मेरी आवाज आ रही है क्या आपको?
Ma'am, I think
Sir,
remove your
sir.
earphone.
Rasika, you are not audible. Sir, you are audible properly.
Okay.
Yeah. From the beginning.
No, it's okay. Just last 2-3.
Okay, sir, fine. He is a chairman of Board of Studies as well as Department Academic Quality Improvement Council. He is presently involved in writing one book on antenna technology. Also, he is holding key position in the research core team of the institute. We are having such a distinguished personality among us to deliver the session on mmWave band antenna design and optimized for 5G frequency band at 26 GHz. On behalf of Department of Electronics and Telecommunication Engineering, Vivekanand Education Society's Institute of Technology, and on behalf of all the participants from various states, we welcome you, sir, for today's session, that is day 2 of Atal FDP. Thank you, sir, for your valuable time. Now I request you to conduct the session. Over to you, sir.
Thank you so much. I'm audible to everyone?
Yes, sir.
Am I audible? Okay. So I'm going to share my screen. My screen is visible to everybody?
Yes,
Yes,
sir.
sir.
Yes.
Yes, sir.
Okay, so I'm going to continue from this point. Myself, Dr. S.K. Jain, working as a professor and head, as I have been introduced by Ma'am Rasika Nayak. So my talk is millimeter wave antenna design and optimized for 5G band, 26 GHz applications.
Satish, sir, sorry to
Yes.
disturb you. Can you
Okay.
put your presentation in the presentation mode?
Presentation mode, I am presenting, my screen is there.
No, you are presenting with the PPT.
Sir, full screen mode.
Full screen mode.
Okay, full screen, right. This? Is it
Yes,
clear
sir.
to everybody? Okay.
Yes, sir.
So thank you so much. Thank you, Department of Electronics and Telecommunication Engineering, Institute of Technology, Vivekananda Education Society, for giving me this chance to deliver my talk in Atal FDP, 1 week FDP. on millimeter wave technology. So my talk topic today is millimeter wave antenna design and optimized for 5G band applications. There are few bands available for 5G. 26 gigahertz is one of the bands available in India. So I will focus on this. But before that, some basic would like to discuss about the antennas. I hope all the audience are familiar with the basics, so I will not take much time, but I will try to show at least and a little bit give some brief information. So a few points which I have outlined as an introduction. That's frequency spectrum, etc. I will discuss in this. Then types of the antennas and planar antenna technology, then antenna performance parameters, then millimeter wave antennas, then 5G antenna design strategy, then results and discussion, then conclusion and references, then current antenna activities. Other than that, which is going on in house, I will prefer to discuss at last. Then acknowledgement. I will start from the frequency spectrum. Everybody is understanding the meaning of the frequency spectrum. Frequency scale I have shown over here. On that scale, number of segments has been created. And some number I have put over there, like 3 kilohertz, 30 kilohertz, 300 kilohertz, 3 megahertz, till 300 petahertz. And
Sir,
who,
slide is not moving, sir. Slide is
pardon,
not moving. Slide is
slide,
not moving.
now it's moving.
Sir, your
Yeah,
slides,
now,
yes,
yes,
now it is visible.
interesting.
Yeah.
It's visible.
Yes,
Yes,
sir.
sir. Yes, sir. Now it is visible.
Now it's visible.
Yes, sir. Yes, sir. Now
Sir,
it
now
is
it
changing.
is.
Okay. Is it changing now?
Yes,
Yes,
sir.
yes, sir.
Okay. So presentation outline I've just directed, like frequency spectrum, types of the antenna, planar antenna, antenna performance parameters, then millimeter wave antennas, then 5G antenna design strategies, then results and discussion, then conclusion references, then current antenna activities going on in house. I will prefer to talk that. Then acknowledgement. Now, are you able to see this frequency spectrum slides?
No, sir.
Sir,
No, sir.
we can see
No.
presentation outline wala slide.
Uh,
Now it is.
outline.
Sir, you please join once again. Just stop sharing the screen and once again start.
Okay, right. Through this.
Sir, put the slides in PPT
Slide.
mode, full
Slide show
screen,
mode, sir.
full screen screen mode. mode.
sir.
Yes, sir.
Hello, sir.
Hello, sir. Hello, sir. Hello, Satish, sir.
Sir, you're not audible. Hello.
My voice is coming to you.
Yes, sir.
Now,
Now it is
now
coming.
it is
Okay.
coming.
And my slides, are
Sir,
you
Sir,
able to
slides are
see?
visible, but it is not to the full screen.
Full screen mode I have done, ma'am.
No, no, please put it in slideshow.
Slideshow I'm putting.
yeah, sir, actually you pressed the slide show, but it is not showing there. It is not reflecting.
Sir, actually, when you share the screen now, while sharing, share the entire screen. So,
Okay.
so you
Yes,
Share.
sir.
stop share and then again share the entire. While sharing, you select entire screen.
Okay, right. No, entire screen, but okay, right. Uh,
Sir, certain
entire.
broken windows will come. You please share that one, sir. Broken
Okay,
windows will come, sir.
okay,
That will be a right mode, sir. Yes, sir. Yes, sir.
right.
This is the right mode. Yes,
This
sir.
is the right mode.
Yes,
Now,
sir.
Yes, sir.
okay.
Yeah, yeah, yeah,
Now it
sir.
is visible.
Now it's
Yes,
correct,
sir.
sir.
Okay, right, right. So
Thank you, sir.
frequency spectrum is a very important aspect of any communication systems. So as we go ahead from 3 kilohertz to 300 petahertz, the frequency is increasing, and there is a relationship between frequency and wavelength. When the frequency increases, the wavelength decreases. So at 3 kilohertz, the wavelength is 100 kilometer, and at 300 petahertz, the wavelength is 10 nanometer. And here number of bands are available, like very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extra high frequency. Then infrared band is there, then visible band is there, then ultraviolet is there. So like this, these bands are called basically the radio frequency bands, and these are having some micro band also. And millimeter band also. So these millimeter band start from 30 gigahertz to 300 gigahertz, and there are a few more bands available which are being applied for satellite and radar communication. Like L band is there 1 to 2 gigahertz, S band is there 2 to 4 gigahertz, C band is there 4 to 8 gigahertz, X band is there 8 to 12 gigahertz, KU band 12 to 18, K band 18 to 27, K band 27 to 40 gigahertz. Then V band is there, then W band is there from 40 to 110 gigahertz. So these are very important bands. I'm going to focus my work on 5G band, which is a 26 gigahertz. But before that, I will show how to design the antenna, which is working for a millimeter wave band, that is 30 gigahertz to 300 gigahertz. So next slide is the basic communication systems. As we all understand, the basic communications. In communication, there is a transmitter, there is a receiver, and between the transmitter and receiver, there is a channel. It could be a physical channel or it could be a non-physical channel. Of course, noise source has to be added in both cases. So now question is, where is the antenna located? So for antenna, you have to understand the transmitter section. So here, the signal which is to be transmitted through the antenna has to be modulated. So our information is a modulation in. Then this has to be amplified through the voltage amplifier, then power amplifier. Then this has to be associated with the carrier signal. So crystal oscillator is there. This is to be amplified through the voltage and power, and it has to go finally to the RF output. So from in RF output, the information signal, which is a modulating signal, is to be grouped with the carrier signal, and this whole signal is called the modulated signal, which is transmitted through the antenna. So this is the role of the antenna basically. Antenna radiate the signal toward the receiver side. Now let us talk about the types of the antennas. Types of the antennas are available, like wire antenna, like aperture antennas, then microstrip patch antennas, then array antennas, then reflector antennas, then lens antennas. So these are the pictures, like a dipole antenna, circular or square loop antenna, then helix antenna. These are the example or category of the wire antennas. In all three, you can observe the wire is being used. For dipole antenna, particular length wire has been used. When this wire is to be in circular shape, then it becomes the circular loop antenna. And when this wire is in the helical form, and when we excite it from the one end, then it becomes the helix antenna. And here, remember, in case of dipole antenna, length and radius plays an important role as far as the performance is concerned. In circular loop, the radius plays an important role. In helix antennas, The number of loops are there, the distance between the loop, then diameter of the loop, then diameter of the helical tube. So these are the parameters on which the performance of the helical antenna depends. So moral of the story is any antenna which is going to give you certain performance, its performance basically depends on its geometrical parameters. So if you want to design an antenna, you have to optimize these geometrical parameters. Similarly, second category of the antenna is the aperture antennas. In that, pyramidal horn is there, the conical horn is there, then rectangular waveguide is there. Then third one is a microstrip patch antennas. In microstrip patch antennas, number of configurations can be used as a microstrip patch, but I have shown here just two. One is the rectangular microstrip patch antenna, and second one is a circular patch antenna. Other than this, there are few variables or parameters I have shown over here on which the performance depends. Like microstrip patch antenna having length and width, and thickness of the copper, then height of the dielectric sheet, then the dielectric constant of the material which we are using as a substrate. So on these parameters, the performance of the antenna depends. Similarly, same thing is with the circular patch antenna. Here, radius plays an important role. So only the radius is one of the variables which need to be taken care of. So, and other array antennas are also there, like Yagyu antenna. Number of elements we have to group in a particular fashion with certain distance and length. These are the reflectors, these are the directors, and the main antennas here, which is excited by the micro source. Right. So this is Yagyu antenna, and Yagyu antenna we are say one kind of antenna array in which the number of elements group together to get the desired performance, like gain, etc. Similarly, microstrip patch array is there. Number of microstrip patches can be etched out in a particular dielectric sheet. So they form the array. Similarly, aperture array is there. In any particular metallic sheet, if you make a certain slot, then all the slots will act as a array antenna. Similarly, slotted waveguide array. In waveguide, on the surface of the wall, you can create some slots. So they become finally the slotted waveguide array. Then reflector antennas are also there. This is a parabolic reflector with front feed. Then this is a parabolic reflector with Cassegrain feed. Then this is a corner reflector. Here, the reflector fundamental is based on this particular parabolic equation, where if you keep at the focal point a certain source which is radiating the signal will come to the surface of the reflector and it will get reflected back, and all the reflected signal will come in parallel. It means they are ending to the infinite. So this is the reflector antenna. The vice versa is there. If the signal is coming from the infinite, they will come to the surface of the reflector antenna, and finally this has to converge at the focal point where the receiving antenna you can keep. So higher gain you are going to get through this, right? So the reflector antenna. The next one is the lens antenna. Lens antenna. Lens we have already studied in physics in schooling. Okay, so as it works on the light, and light is also electromagnetic wave. Okay, so that can also be used to transmit the signal. So convex plane lens antenna is there, then convex is there, then convex concave is there, then concave plane is there, concave is there, concave convex is there. These lens are having the index of refraction greater than 1, and these antennas, convex plane, concave, convex, they are having refractive index less than 1. Now, let us come to the planar antenna technology. Uh, Nowadays, the researchers and designers, they are they are putting effort to design and develop and experimentally measure the planar antennas. Planar antenna means microstrip patch antenna is one of the planar antenna. Uh, just few slides back, I have shown the different type of antennas, like reflector antenna is there, then aperture antennas are there. One thing you might have observed in them, that they are three-dimensional antennas. They are not planar antennas. They are three-dimensional antennas. They are having certain weight, they are having certain volume, and they are bulky also. So in certain applications, they may not be useful. Like if you think the application of the rocket, in rocket you cannot put a reflector antenna, parabolic reflector, etc., because of a lot of problems, especially the aerodynamics, etc. So for that you require the antenna which can take the shape of the rocket surface, like planar antenna. If you take the planar antenna, easily you can paste it on the surface of the rocket, because rocket when launched, you need to track it, and for tracking you require the antenna. Antenna has to send the signal, right? So signal, so rocket, on the surface of the rocket you have to put the antenna in the metallic body. So now question is so it is called the conformal actually. So what you have to do is you have to use the flexible planar antennas, or flexibility you can create by the using the substrate having the flexibility like foam, etc., right? So it is a typical microstrip patch antenna 3D view. There is a patch, there is a substrate, and below the substrate there is a ground plane, and these are the dimension of the patch antenna. You are feeding from this point. Okay, so this is a excitation point, right? So this is a 3D view of one of the planar antenna, that's called microstrip patch antenna. This is cross sectional view of this. From the top you can see this is a length, this is width of this antenna. You are feeding from this point, and if you see the side view, you come to know this antenna has been excited by the coaxial feed. In coaxial, there is a center conductor and there is a outer body. Outer body you can connect to the ground plane, and center connector you can extend to the patch. So when you connect the micro source send the energy come to the patch get excited, and patch release the energy which gets radiated into the atmosphere, right? So this is the mechanism also. So these are the planar antennas nowadays preferring. Engineers and designers and researchers, they are working on it a lot since 20 years. A lot of research is happening because a lot of applications are there where these antennas are equally useful and giving the remarkable performance, right? Let us talk about the feature of the planar antennas. Why planar antennas are being preferred by the researchers and designers? These are preferred because of lightweight, low volume, low profile, planar configurations which can be made conformal. Conformal means they can take the shape of the object, like rocket's surface. If the flexible dielectric sheet you use, you can paste it on the surface of the rocket, and you can utilize them for reception and transmission. Then it can be made thin, hence it does not perturb the aerodynamics of the aerospace vehicles, right? If you use the 3D antenna on the surface of the rocket and rocket is moving in space, a lot of aerodynamics effect will come into this. And so a lot of disturbance you will get, so that's not possible. So what is to be done is you have to prefer the thin and little bit flexible antenna. So that is possible by planar technology only. It can be easily mounted on missiles, rockets, and satellite without major alterations, as I discussed right now. Then circular polarization is possible, the simple change in field antennas. Actually, what is happening is most of the antennas we discussed, they are linear antenna, right? And nowadays there is a trend of using the circularly polarized antenna. Because if the antenna is circularly polarized, irrespective of the position and location, we can use them easily, right? So, circular polarization is possible with simple change in feed positions. So, in these antennas, some sort of changes if you create, you can have a circular polarization. In general, the antennas are linearly polarized. We will discuss in our later ahead in a few slides. Then these antennas, planar antennas, are compatible with design like solid state device, like oscillators, amplifiers, attenuators, switches, modulators. ये जो है ऑसिलेटर्स है, एम्पलीफायर है, अटेन्यूएटर है, स्विचेस है, दे आर आल्सो ऑन प्लेनर टेक्नोलॉजी, right? The oscillator you can develop on dielectric sheet, amplifier you can develop on dielectric sheets, attenuator you can develop on dielectric sheets. So when these micro components and devices are being developed on micro dielectric sheets, so naturally antenna can also be developed on same sheets. So they are compatible with the design. In antenna, you have to feed it, so you require feed lines, and matching is required. So matching network you have to use. Okay, so they can also be fabricated simultaneously with the antenna structure, right? So this is one of the feature of this. And other performance can also be achieved in planar technology. Like if you want to develop the dual band antenna, or you can you want to develop the multi-band antenna, you can easily do it, right? You can have a broadband antenna, you can have a miniaturization, you can have a other performance parameters, you can easily incorporate into them. So that is the beauty of this planar antenna technology, right? Now, there are, in spite of these advantages, there are few disadvantages also. Like these antennas are narrowband antennas. Their bandwidth is very narrow, 1 to 5%. So why you have to create some changes into them. Radiation into the half plane only. Why? Because there is a ground plane. On the ground plane, there is a dielectric, and at the top of the dielectric, there is a patch. You are exciting, it is radiating. Now, radiation is in half semicircle only, right? Hemisphere. Radiation cannot go in opposite direction because there is a ground plane, so field cannot penetrate to the ground and go in other direction. So it is the disadvantage of it. So radiation is into the half plane only. Then end fire performance is poor. Antenna radiates in only in half plane towards the upper side. And side, you have to do a lot of work as far as the antenna design is concerned if you want to have a poor end fire performance. Okay. Then power handling capability is very low of these antennas because you are developing the small antennas. So if you think about the power level, they are working in milliwatt or microwatt, something like that. But for heavy use, you require an antenna which can handle the power in kilowatt or megawatt, etc., especially for space applications. So you have to develop the antennas accordingly. Of course, that is possible using with the microstrip patch antenna, having planar technology. Then spurious radiation is possible from the feed networks. You are developing the feed line. You are developing the matching networks. When the power flows through them, some sort of radiation is possible from them. So that is called the spurious radiation. That is unwanted one. So that is one of the negative point. Then the permittivity which you are using in substrate, that is actually temperature dependence. So when the antenna is being used in different location, due to the temperature difference, the behavior of the dielectric sheet may change. So the performance of the antenna will get affected. So that is then another surface wave curve. So therefore, these all due to these all problems, the design and fabrication has to be very very carefully done. Right? There are few applications I would like to discuss in this. Like they are used in satellite communications, they are used in Doppler and other radars, they are being used in radio altimeter or missile telemetry, they are being used in man-pack equipment, they are being used in environmental instrumentation and remote sensing. Then they are being used as a feed element in a complex antennas. Right? Now, different patch configurations are there. Like in planar technology, you are using the microstrip patch antennas. Right? A microstrip patch antenna, there is a patch, microstrip patch on the dielectric surface or substrate, which is called substrate. Right? Now, question is what shape you can choose as far as the patch is concerned. So there are few conventional configurations, there are few complex configurations. You can have a square shape of the patch, you can have a disc shape of the patch, that is a circular patch. You can have a rectangle shape, you can have a elliptical shape, you can have a ring, you can have a equilateral triangle. These shapes are being preferred nowadays because they are regular and they're involving very less number of variables. If you see the square, only one variable is there. If you see the rectangle, there are two variables. If you see the disk, it is having only one variable. So like this, if you see the equilateral triangle, there is one variable. That is the length of the side. Right? So optimization is easy if you use the conventional configuration of the patch. But in complex configurations, if you see the disk with slot, semi-disk, disk sector, then the pentagon, U shape, S shape, L shape, then T shape, then cross junction, then trapezoidal, then rectangle ring, like this. So because of this, you see, because of the structure configuration of the antenna, the variables are more number of variables because you are creating a lot of changes in geometry. So they involve the number of variables and optimizing number of variables altogether at the same time to achieve the certain performance parameter performance from the antenna. It's quite a difficult task, right? So that is a very hectic and tedious and cumbersome. So complex configuration is to be discarded. So in general, most of the time, the researchers and designer are preferring the regular shapes because of the less number of variables involved. Now let us come to the radiation mechanism of the microstrip patch antenna. This is a very important information I would like to share with all of you. Here, this is the microstrip patch you can see, and this is the width and this is the length. Along with the width, field is not changing. You can see here, but along with the length, the field is changing through the halfway. It is going upside and the low side. So it is a half wavelength, L equal to lambda by 2. So half wave only, the field is changing. This is in this side and this in this side. Here, this in this side and in this side, right? So here you can see along with the length, the field is changing. And other than this field, the field is also terminating on the ground plane from the patch in this manner. So it is in this direction. So this is called the fringe field, which is available, which remains in the free space for a certain duration and gets terminated, right? So the direction of this fringe field is in this direction. Direction of this fringe field is in this direction, right? And as far as the voltage and current is concerned, as I told you, this is the length of the patch. This is the width of the patch. You can think patch like line. If you connect the points, it becomes the line. If you connect the number of lines, then it becomes the surface. And if you connect the number of surface, then it becomes the 3D structure. So if you join the number of lines, you can think number of dipoles. If you join, you get the patch, right? So this is the length of the dipole or length of the patch. So at the center, the current is maximum. You can see here. It means the impedance is 0. And here the current is 0. So it means the impedance is highest. And here voltage is high and voltage is minimum at the center. So current is maximum, so voltage is minimum. Current is minimum, so voltage is maximum, right? So here voltage is maximum, it means impedance is very, very high. So zero impedance you will get at the center, and here nearly you will get 300 ohm. So you have to optimize the location of this length where the impedance you are getting the 50 ohm to 75 ohm. Otherwise, due to the high mismatch, the power will get reflected back. So efficiency of the antenna will fall down, right? Is it clear to all of you? I think so. Radiation occur from the fringing fields, which can be enhanced by increasing width W, right, increasing the substrate thickness, or by decreasing the permittivity. Feeding techniques. There are few feeding techniques available to excite the microstrip patch antenna. One is the coaxial feed. In coaxial feed, what we have to do is we have to drill from the downside in such a way the drill reaches to the patch. And when you connect the coaxial coaxial connector, the inside connector is to be inserted in such a way it reaches to the patch where it can be soldered. And the outer body of the connector can be connected to the ground plane, right? Second one is a microstrip line feed. Here, this patch is excited by the source through the microstrip line. This microstrip line is acting as a feed line. The problem with this feed line is it is connected with the edge of the microstrip patch, where the impedance is very high. Whereas the impedance of the microstrip line is 50 to 75 ohm. So due to this 300 ohm and 50-75 ohm, there is a high mismatch between this and patch. So because of this high mismatch, the reflection is taking place in a high amount. So the efficiency of the antenna is falling down. Okay. So what we have to do is we have to create a slot here, right? That is called inset feed, right? So what happens when you insert this till and this point and you create some sort of opening here, then this is possible to excite the antenna at the from the location where the impedance is matching. I mean 50 to 75. Third one is a proximity coupling. Here you are exciting the antenna through this microstrip line, and this microstrip line, there is no direct connection of this patch, radiating patch. Radiating patch is a little bit upper side. So there is the electromagnetic coupling between this microstrip line and the patch. So patch is getting excited and it is radiating. So this is a proximity coupling. The most important feeding is the aperture coupled feed. You can see here the same microstrip line is there, but between the patch and microstrip line there is a slot which is made on the ground plane or some sort of metallic body. So what happens when you excite this microstrip line through the micro source? The coupling happens between this microstrip line and microstrip patch through the slot. In fact, the slot is also acting as an antenna, right? Slot is also antenna. So there are two antenna now. This microstrip line antenna, microstrip patch antenna, and this slot antenna. Is it clear? So what is happening is now two antennas are playing the role. So when they play the role in a particular fashion, then they become the broadband antenna. So broadband behavior you can achieve through the aperture coupled feeding method, right? Now let us analyze the antenna. The microstrip antenna can be analyzed by two ways. Right? One is a transmission line model. Second one is a cavity model. In transmission line model, we can assume the microstrip patch is a transmission line where we are feeding it. This has to be represented by these two part of this model, right? And here, since there is a voltage maximum at the end of the microstrip patch, means where the edges is there. So at the edges, microstrip line at the edges there, since the voltage is maximum, so you can think it is as a slot, and this slot is equivalent to RC circuit. So R and C parallel. Here R and C parallel. So at both end RC network is there, right? And in this way you can find out the input impedance, right? Here you can see the resonant input impedance G1, G2, the susceptance B1, B2. They all are function of width, length, and height, etc. These are the parameters which gives you the value of this. As far as the resonant frequency is concerned, resonant frequency is to be given in this particular transmission line model by 1 upon 2 L effective, epsilon R effective, mu 0, epsilon 0 under root. And L effective is the effective length of the antenna, because there is a fringe field. So it means it appears that the length of the antenna is little bit larger than the physical one. So L is the physical length, and the extension of the length is del L. So L effective is L plus 2L, right? So in this way, you can find out the resonant frequency of this particular using this transmission line model. Now, cavity model, what we have done is we have considered antenna as a cavity, because cavity is nothing but some sort of confined area that's completely closed, like waveguide. Waveguide is open at both hand, right? But when we close it at both hand, if we short it, then it completely closed. It's something like box. Then it becomes the cavity. The same way we can think the antenna. Antenna, our antenna is also like that. We can consider it a cavity. So this is the length of the antenna, this is width of the antenna, and this is the height of the dielectric. So it is a some sort of cavity, right? In case of cavity, the resonant frequency is to be given by this. Whole derivation is there, of course. Lengthy derivation is involved, but it is very easy to understand. It is available in the book. I've taken it from the Balanika book. It is very, very standard book. It is easily available nowadays. So these are the resonant frequency. If you simplify further for this particular domains 0, 1, 0, particular mode 0, 1, 0, 0 xy means y direction, right? Radiation is in the y direction, suppose. Sorry, field direction is the y direction in that case, and radiation is in x direction. So FR 0, 1, 0. So resonant is 1 upon 2L mu epsilon under root. That is V0 upon 2L under root epsilon r. Some important characteristics of the antennas are available, which I used to prefer in my design. Actually, when I design the antennas, I ask my student, please focus these points, because these points are very, very important. Of course, there are some more performance parameter available in the book, but experimental point of view, these parameters we go, and their verification easily can be done experimentally. So directivity is there, gain is there. I'm not going in definitions actually. These definitions are available in the book, and I think this whole micro community understand them, right? So this is the directivity, this is a gain, resonant frequency and bandwidth, then dual frequency and multi-frequency behavior, then polarization diversity characteristics like linear polarization, circular polarization, then elliptical polarization, then circular polarization, again right hand circular polarization, left hand circular polarization, then miniaturization is there, then main lobe direction is there, then axial ratio is there, then half power beamwidth is there, then efficiency is there, then E and dash plane radiation pattern is there, 2D and 3D, then a specific absorption rate is there, then side lobe level is there, then front to back ratio is there. So these are the important parameters. As far as bandwidth is concerned, for linearly polarized antenna, percentage bandwidth can be calculated by its parameters H, W, L, lambda 0, A is the constant. It is having certain value. Similarly, for circularly polarized antenna, the bandwidth can be defined by AR minus 1, QT, A under root AR. AR is the axial ratio, and QT is the quality factor, which can be, which need to be derived mathematically. Some important radiation pattern. Let us understand the radiation pattern. Actually, there are when we go for testing the antenna experimentally in anechoic chamber, I used to tell students, please understand the meaning of E plane and H plane exactly, because this is quite confusing. Because we are using the horn antenna as a reference antenna, standard gain horn antenna. So this is I need to show these slides. These are very very important to all of you, especially those who are newcomer in this fraternity, microwave community. Right. So principal E and H plane radiation pattern, if you want to understand, then you have to understand this diagram. Right. So this is X, Y, Z, and suppose some antenna has been kept at the center and radiation pattern is something like this. There is a major lobe, minor lobes. So you have to understand what is the phi. So phi is starting from the X, and along with Z you have to rotate. So the phi is 0 to 2 pi. And question is, what is the theta? So theta is starting from the Z along with Z. When you go away from the Z, the theta increases, and the maximum limit of the theta is other side. If you come here, it makes the 180-degree. Right? So theta limit is 0 to 180-degree. Right? But if you plot the radiation pattern in polar, so you have to just make the double of it. You have to take the replica of it. So it becomes 0 to 180 and again 0 to 180. So in circle, 0 to 360-degree, you can plot the radiation pattern for E plane and H plane also. So here you can see the radiation pattern of this horn antenna. If you excite the horn antenna, it will radiate the signal. The lobe is getting formed. And here you can see here, this is E field and this is the H field. This is H field, this is E field, right? E field, H field, E field, H field, right? So this is called H plane which in which having the H field, the called H plane. The plane which is having E field is called E plane. So E plane is this, H plane is this, and this is whole radiation pattern is three-dimensional, and it is moving in X direction, right? So this way you can think. Here it is quite tricky. When we ask the students what is the E plane and H plane in case of dipole antenna and microstrip antenna, it is quite tricky. We have to understand it. So let us say it is a dipole, right? It is a phi, right? So when you rotate phi 0 to 2 pi and you see from the top to downside Z along with Z, then you will get the circle. So that is the H plane, right? But when you see either from X or Y or some other direction, any phi, if you change the phi and C toward this, then you will see the definite shape, something like this, 8 shape, horizontal 8 shape. So that is the E plane of antenna. And any side you see either from this side or this side or this side, you will see the same structure. 8 you are going to get definite shape. This is called definite shape, right? So this shape is going to give you the E plane radiation pattern. So there is a H plane. If you see from the top, you will get the circle. If you see from the side, you will get the definite shape. So definite shape is the E plane and circle is the H plane. So this is with dipole antenna. So for understanding the E plane and H plane, you have to understand first the mechanism of the antenna. It is not same for same approach for all antennas, right? It is different for different antennas, right? Now let us talk about the bandwidth. The bandwidth of the antenna can be increased by many ways. Number of elements you can keep in same plane like this, right? So they couple with each other and they increase the bandwidth. Another way is if you don't have a space in horizontal direction, then you can keep number of antennas one above the other. This is called a stacked patch antenna pattern, right? So in that also you can increase the and bandwidth. You understand? This is the reflection coefficient plot f2 minus f1, right? This is absolute bandwidth, but f2 minus f1 upon fr is the resonant frequency, and if you multiply 200 the percent, then it becomes the bandwidth in percentage. So bandwidth in percentage and absolute bandwidth, there are two bandwidths in trained as far as the design of antenna is concerned, right? Now let us come to the main topic, main theme of this Atal FDP, that is the millimeter wave antennas, right? So we started from 6, so it's 45 minutes. My voice is reaching to everybody.
Yes, sir. Yes, sir.
I am audible.
Yes, sir.
If you want to correct me somewhere, and you can suggest me so that I can rectify it.
Yes, sir. Sure.
I am running well.
Yes, sir.
Yes, sir.
All well,
Okay.
sir.
Okay, okay. My points is clear to all of you, I think.
Yes, sir.
My flow could be a little bit different, but I expect all of you to grasp it. It is very, very important information. So now I'm coming to the millimeter wave antennas. Right? Nearly 36 slides are there in my this all presentation. So I think half time is over. A little bit more half time I will take 45 minutes. Then I will complete it. I will pack up.
Yes, sir. No problem.
Okay, so millimeter wave antennas. I shown a lot of slides so far. They are useful to understand the antenna and design concept also. Once you understand them, then it is easy to understand the millimeter wave antenna design. Okay, so I don't let us not think this manner. Ki what is use of this E plane or H plane or bandwidth and this and that, because all fundamentals are useful. And antenna, the beauty is every fundamental is useful, because you have to design the antenna, you have to estimate the bandwidth, you have to estimate the resonant frequency, you have to see the polarization, whether it is linear or circular polarization. If it is circular polarization, then it is a left hand circular polarization or right hand circular polarization. You have to estimate the E plane or H plane radiation pattern. You have to understand the gain, you have to understand the directivity. Even, my if I ask my students, madam, they sometimes they are not able to answer in viva what is the bandwidth, this gain, and what is the directivity and how they are related. They are getting confused. If they answer just from the book, even then they have some problem, because they don't understand exactly what is the gain and what is the bandwidth. Actually, what is directivity? Actually, though, in antenna, until unless we do the things experimentally, the concept will not be clear. Even if one parameter, that is efficiency, this also creates some problem. Simulation tells something about the efficiency. There are two type of efficiency. There is a radiation efficiency, there is a reflection efficiency, there is a total efficiency. So they don't understand. Some plots are coming, they do not understand what is this actually, how to read them, how to estimate. So fundamental is very, very important in antennas. Once the fundamental is clear, you can be a very good designer actually in antenna, right? So let us come to the millimeter wave antennas. Millimeter wave frequency band is there, as I discussed in frequency spectrum in very first slide. The range of the millimeter is 330 gigahertz to 300 gigahertz. So millimeter wave antenna are being designed within this frequency range only, right? Now there are applications.
Sir, you are not audible. Hello, sir. Hello, sir. I think sir is disconnected.
Okay, no problem. Let me talk. Let me call him. Yes, sir is joining in sometime.
Yes, madam.
I'm sorry, 2 3 minutes. Some issue happened.
Yes, sir.
It's okay, sir.
No
No problem.
problem.
Now screen is visible to ma'am. to all of you?
Yes. Yes, sir. Yes, sir.
It is a millimeter wave antenna design.
Yes. Right, sir. Yes.
So millimeter wave frequency band is 330 gigahertz to 300 gigahertz. आई एम श्योर आगे जो स्लाइड्स आने वाली हैं वो बहुत यूजफुल रहेंगी, सभी के लिए बहुत एक्साइटिंग रहेंगी. सो अभी आप लोगों ने अभी फंडामेंटल देखा है अभी शुरू की स्लाइड्स में, तो वो आप लोगों को शायद इतना एक्साइटमेंट नहीं रहेगा, क्योंकि आप बुक्स में देखते रहते हैं, डिस्कस करते रहते हैं, स्टूडेंट्स से इंटरेक्ट करते हैं. बट अभी आगे जो स्लाइड्स आने वाली हैं दे आर वेरी वेरी यूजफुल एंड वेरी आई मीन माइंड ब्लोइंग, I will say, in antenna design perception. So millimeter wave frequency band start from 30 gigahertz to 300 gigahertz. Nowadays, as I said, the machine learning and internet of things are happening almost everywhere in the world. They are having application in a smart home, okay, having smart appliances, so they need to be operated, so antenna is required for that. So millimeter wave antenna is having application in those areas, right? Then due to rise in data transfer, requirement of millimeter wave band in 5G wireless communication is growing, right? So actually what is happening is nowadays, abhi right now 4G is happening, right? 4G is happening. 4G communication networks are available. Communication is happening through them. So, but the problem is the number of users are growing day by day. So the data transfer is a great issue. So the vendors are shifting from 4G to 5G communications, and they have to be dependent on millimeter wave frequency band antennas, right? The 800, 900 megahertz, 1.8, 2.1, 2.3, and 2.5 gigahertz bands are currently used by the 4G networks, right? So right now till 2.5 gigahertz we are packed, right? But when we go from 4G network to 5G network, then we have to think some other way. Okay, because 4G networks are not able to cope with the requirement of large bandwidth. What is happening is when the number of users increasing, they require their own frequency band. So due to the, and more applications are coming now every time, right? YouTube videos are also coming. Then share activity is going on. So many apps are coming, right? So audio and video, so many things are happening. Business is happening through the mobile, right? So this all activity requires a large bandwidth, right? So 4G network is not able to cope with that, right? So therefore mobile operators are shifting to the 5G network, and 5G network covering the millimeter frequency band like 600 million megahertz, 700 megahertz, 3.4, 3.67 gigahertz, right? These frequencies are not, of course, millimeter band, but 26 gigahertz is one part of it, right? So one band they additional they are going to utilize. This band is somewhere near to a millimeter band. Actually, this is sometimes this is also called millimeter band, right? So researchers are shifting focus toward the antenna design in millimeter band. This is my research is getting started from this point actually. Millimeter wave antenna design and optimization. Now, question is how to design the millimeter wave antenna, right? So I have chosen microstrip patch antenna. In that, I have taken the circular patch. In that, dielectric sheet is there, ground plane is there. On the upper side side of the dielectric sheet, there is a circular patch which is feed by inset. I mean, there is a cut, right? And in the cut, the microstrip line is to be inserted as shown in the figure. You can see here. Okay, so the number of variables are there now, right? The substrate length is there, substrate width is there, right? Slot width is there, then slot length is there, right? Then feed width is there, then feed length is there, right? Substrate height is there, dielectric constant of substrate are there. So these are the parameters. Then radius of the patch is there, most important point, right? So this is a copper patch and radius circular patch, so it will have a certain radius or diameter, you can say, right? So these are the variables on which the performance of the millimeter wave antenna will depend, right? So this is the geometry of the millimeter wave antenna. I think everybody is familiar with this geometry now. Okay. So in this work, what we have done, that I'm going to show you. So we have designed and developed microstrip circular patch antenna in millimeter frequency band. Circular patch antenna has been optimized through hit and trial method, which is greater than 30 gigahertz, because the micro millimeter band start from 30 gigahertz, right? By parametric analysis, dimensions are set in such a way the antenna resonate at 26 gigahertz, so that it can be utilized for 5G communication band, right? Now there are few performance parameters which we have estimated, like reflection coefficient, like Smith impedance plot, then E and H plane gain and directivity, radiation pattern, then axial ratio, then main lobe direction, then half power beam width, then side lobe level, then efficiency. Okay, these all parameters we have explored after designing, right? Antenna has been fabricated in a laboratory and experimentally measured for the reflection coefficient and other parameters. Is it clear? Now, suppose we want to develop, so far we have discussed the circular patch antenna, but suppose the task have been given to develop, design and develop the rectangle microstrip patch antenna. Then in that case, you have to understand the geometry of it, right? So this is length and this is width, right? And the radiation pattern is something like this. Okay, this is X, this is Z, this is Y. So microstrip patch antenna will have a E plane and H plane radiation pattern. E plane radiation pattern is on XY. So this is X and this is Y. So in this plane, X and Y. So this X, this is Y and this is X, right? So this plane will have a E plane, and X and Z. So this is X and this is Z. So in this plane, it is going to give you the H plane radiation pattern. Okay, H radiation pattern cannot be parallel to the patch. You have to understand it, because this is not conceptually correct, right? So one plane is both plane is perpendicular to the plane of the patch, so that is the E plane and H plane, right? So these are the equations which can be utilized to find out to calculate the electric E plane radiation pattern and H plane radiation pattern in case of this microstrip patch antenna, rectangle microstrip patch antenna. And these are the equations, right? This is inside feed microstrip patch antenna. At the edges, the impedance is very high, 300 ohm. At the center, it is 0. So you have to optimize the location between 300 ohm to 0. So this after optimize, the location is this. So at this point, either you excite it by coaxial field or by inside feed, a microstrip line feed, right? This feeding this way is not correct, because you are feeding through the edge. So at the edge, the impedance is 300 ohm, right? This is length, and since there are fringing field, so there is a extended length. So del L, so 2L, right? So now question is how to design rectangle patch antenna. So you require some equations. You can find out epsilon r effective. You have been given epsilon r because you are having dielectric constant material, which is having certain height. You cannot change the height. Okay, so you have to lock it. You have to fix it. It is not a variable. Epsilon r is constant. So you have a epsilon r, you have a height h. Now you require the width of the antenna. You don't know the what could be the length and what could be the width. So you have to find out both. So first you find out you have a epsilon r ka value. So and you are told, suppose you have to design the antenna for 40 gigahertz. So FR4 is a 40 gigahertz. Mu 0 epsilon 0 is nothing but related with V0, because V0 is nothing but 1 upon under root mu 0 epsilon 0, right? So from this equation, you can find out W, that is the width of the antenna. Epsilon r and W ka value, if you keep over here along with H, you will get the epsilon r effective. Okay? Then after epsilon r effective and W and H, if you keep in this formula, you will find out the extended length, that is del L. After finding the del L and L, you can find out from here. You have been given suppose 40 gigahertz. So V0 is 3 into 10 to the power 8 meter per second. Epsilon r ka value you have been given, let us say 4.4, epoxy glass, PTFE, polytetrafluoroethylene, right? So L you can find out from this. So if you keep the L, so you will find out the L effective. So this is the total length, effective length of this antenna, right? Now you have found length, you have found the width. Now question is how to find out the depth of feeding. This Y0, how you can find out? So Y0 you can find out from this equation, because at the edge you know the impedance is 300 ohm. At here you require the impedance 50 ohm suppose. So 300 ohm equal to 50 ohm, cos square pi upon L. L you know. So Y0 you can calculate right? So this way the feeding location also you can estimate, because these are the variables, these are the parameters which you can vary, right? Height of the dielectric you cannot change, the epsilon r of the dielectric you cannot change, etc. Length of the dielectric you can change, it could be a variable. Width of the dielectric sheet, it can be variable. Patch length, patch width may be variable, feed location may be variable, but dielectric property you cannot change. Okay, and randomly you cannot choose the dielectric material. You cannot say ki I need dielectric material 2.397, because it may not be available in the market. In the world, no company might be producing it, manufacturing it. So whatever the dielectric sheet is available in the market, you have to be dependent on that. And even height, 1.6 is the standard height. Suppose you want to design the antenna with the 3.2 mm, then company will not produce for you for the dielectric sheet having the thickness 3.6 mm, for 3.2 mm. So what you have to do is you have to keep two dielectric sheet together, 1.6 mm, 1.6 mm, and you have to stick it by certain technology, by certain film, dielectric film, and certain procedure is there for fixing them, right? So it will give you the dielectric sheet of 1.6 into 2 means 3.2 mm. So like this, so many constants are there, right? You cannot choose anything randomly as far as the antenna design is concerned. So I think this is very, very important. I shown you design approach of rectangle patch antenna. Now design approach of circular patch antenna. Circular patch antenna we have discussed. This is the circular patch antenna, which we want to develop it for millimeter wave frequency band, right? So now coming over here, our work belongs to from this point. So this is a circular patch antenna. It is having equations FR110 1.8412 upon 2 pi a under root mu epsilon, right? So here you can see these parameters are constant, mu and epsilon. Only a is changing. So a is dependent on resonant frequency. As happens with dipole, if you change the dipole, there is a certain relationship. Okay, f is v equal to f lambda, right? So f is v, so lambda is v upon f. Okay, so lambda is inversely proportional to f, right? And L is lambda by 2. Length of the dipole is lambda by 2. If you have a frequency, then you can convert it into the lambda and you can make it half. So divide by 2, lambda by 2. So it will give the length of the dipole. Similarly here, if you want to find out the area radius, then from the frequency you can find out the radius. Okay, so design is easy because only one variable is involved here. In the rectangle patch antenna, there are two variables, length and width. Of course, feed location is also to be optimized here in this case also, right? So, and moreover, there are fringe field at the edges. So through the periphery, there will be a fringe field, right? So due to the fringe field, the length of will increase. So you have to consider the effective length, that is the area radius. So it is the effective radius AE, right? So FRC 110 is a 1.412V0 2 pi AE. This is the effective radius now, right? So this is the effective radius now. So this way you can find out, and AE is this equation. A you can find out from this equation. A now in order to find out AE, you have to know A, and A is given by this equation. And here F is the variable, constant. So F can be found out from this equation. So once you find out F, you can keep the value of F, you can keep the value of H, resonant frequency, etc., height. So you can find out the physical radius of the circular patch. Once you have a circular patch physical radius, you can find out the electrical radius of the circular patch. And from this equation, which involves the Bessel function, you can find out the feed point location, right? So this is rho 0, this is rho AE, matlab physical. So you have to find out this. So you have been given this value, you have been given. So with the solving this equation, you can find out the same way the feed location in circular patch antenna, right? So you have two parameter you have to find out. One is a location of the feed, another is a radius of the patch. Other parameters are constant. So design is so simple, right? Now, what we have done is we have simulated. We have, with the help of these equations, right? Let us say 30, 40, 30 gigahertz. We find out physical A. Now change the frequency, change the A. You will get the different value of A, right? And with the help of these, we have simulated the antenna, right? In CST, we have used the CST. CST is a computer simulation technology software, right? There are few more software are available, like I3D is also available, right? HFS is also available, right? FICO is also available, right? So Micro Office is also available, है ना? AWR, Antenna Wave Research, Advanced Wave Research, this is also available, right? So many software are available, but CST, I3D, and HFSS are very very popular. CST, I3D is based on the method of movement, right? CST is based on finite difference time domain method, right? And HFSS is based on finite element method. So these are the numerical techniques on which these softwares are based, right? So all are equally important. All software are acceptable. Their work is acceptable in internationally as far as the publication is concerned. Am I audible to all of you? Am I
Yes.
audible?
Yes, sir. Yes, sir.
Yes, sir.
Okay, thank you, thank you. So this way we can design the antenna, right? We can do the hit and trial also. Not only these equations may not be accurately enough to design the antenna. So some hit and trial approach you can also follow. Now, what happens when with the help of these values, and constant parameters like dielectric constant, height of the substrate, and then length of substrate, width of the substrate, then height of the patch, then radius of the patch, then feed location, right? So when you similar you make the layout in CST, and when you go for simulation, you run the simulation, then for three different values, we change the three different radius, and we found the reflection coefficient plot like this. You can see here for radius A 1.5 mm, this antenna is resonating at for nearly 40 gigahertz, that is a millimeter wave band. When you increase the radius, right? So 2.3 mm, because you are increasing from 1.5 mm to 2.3 mm, the frequency is shifting downwards, right? So now antenna is resonating nearly 35 gigahertz, right? Similarly here, when you further increase the radius 2.4 mm from 2.3 mm, this is resonating at nearly 28 gigahertz, right? So we are reaching till 26 gigahertz. So this is called a parametric analysis. What we are doing is we are changing the parameter of the circular patch antenna. And what is that parameter? That parameter is the radius, right? So when you keep on changing, you will get the different performance, right? So this is the reflection coefficient plot with respect to frequency. This is from 20 gigahertz to 50 gigahertz. We have simulated this antenna for 20 gigahertz to 50 gigahertz. Now for all these three, we have plotted the impedance behavior on the Smith chart. So this is 20 gigahertz point. Our all three start. Our initial point is 20, maximum is 50 gigahertz, right? So this is 20 gigahertz. This red one is this red one, right? This black one, this blue one is this blue one, right? And so like this, so all three plots are there. You can see 20 gigahertz and 50 gigahertz, and at the center you can see there is a VSWR2 circle in a Smith chart, right? So this part, which is minus 10 dB below, especially this dip part, right? This is antenna dip, right? Resonance pattern you can see. So below minus 10 dB, it is within the VSWR2 circle. We must understand how to plot this within the Smith chart, right? So this is the parametric analysis of millimeter wave and band antennas, right? Now 5G antenna. Now what we have done is we have reached till 28 gigahertz. So little bit shifted here. So what is to be done? Little bit increase the radius of the patch from 2.4 mm onwards. So we are getting here. Now our radius of the patch is 2.71 mm. And this antenna is radiating 26 gigahertz. That is one of the band which is to be utilized in 5G application. Right? So this is 26 gigahertz point. And here S11 value you are getting minus 43.448 dB. This is very appreciable amount. It shows that the reflection is very minimum. This is a very good design actually. This type of value is very rare as far as the antenna design is concerned, right? And here the same here the impedance behavior we have plotted over here from 20 to 50 gigahertz. Let us say our pattern, this pattern minus 10 dB below part, which is minus 10 dB below, this is within the VSWR2 circle. So here this is 20 gigahertz point, this is a 50 gigahertz point, and this is a 26 gigahertz point, exactly on the line and within the VSWR2 circle, right? Right, and the optimized parameters are listed here, right? So it is a height of the dielectric 1.6 mm, dielectric constant 4.4. These are the constants, not variable. Then length of the feed 2.81 mm. This is okay. This is variable length of the feed because our structure is this, right? This is our structure actually. Okay, so we have to optimize radius, then we have to optimize the feed parameters, length and width, etc., and the slot length and width. So 5 parameters we have to optimize, right? So here these are the constant. These are constant. Length of the feed variable 2.81 mm, width of the feed variable 0.934 mm, slot length 0.52 mm variable, slot width 1.13 mm variable, then radius of the patch 2.71 mm. These are the variables. So first, second, third, fourth, fifth, these 5 parameters are variable here, not only radius. Okay, because we are not feeding it coaxially, we are feeding through the inside feed, right? And height of the copper patch is constant 0.07 mm. Dimension of the substrate we have not we have not make it variable. We fixed it 12.5 mm to 15 mm. And the feed point location, this also we have optimized actually. So these are 6 parameters, 2.19 mm. Okay, so these are the results of 5G antennas. You can see so nice results we are getting in simulation, of course. So far I am showing you the simulation activity. Once the simulation is over, we can go for experimental for validation purpose, right? I will give you sufficient time for discussion, ma'am. Okay, because
Yes, sir.
possible I may finish it a little bit early, so 10-15 minutes you will get to discuss. That is most important aspect.
Yes,
E-plane
sir.
and H-plane. Ma'am, one thing I would like to tell you, all the
Hmm.
results which we are showing to you, they are not ready-made from the simulator. It's not a
Okay.
copy-paste. We have developed from the Excel. You know, these plots are not available in CST or HFS or I3D. These plots are not available. We have developed it in Excel. We have taken the numerical data and we have plotted it. I used to tell my students not to copy it because copying is not a research actually,
Right.
right?
Yes, sir.
Right. So we do hard work along with our students. You see here,
Yes.
this we have developed from the Excel only, right? And if you see the CST or any simulator, their pattern or their figures are typical. If you publish them, everybody can understand this is from CST, this is from I3D, this is from HFSS, right? So this we have to understand it. Everything should be genuine actually, right? So these are the E-plane and H-plane pattern for 5G antenna. Of course, these are the simulated one. We have plotted our own, taking the data from the simulator, right? So this is E-plane and this is H-plane. And from these, you can find out the directivity or gain also, right? So these are the pattern. And E-plane and H-plane, I told you, you can plot it from circle. So this is called the polar plot actually, from 0 to 360, right? These are the performance parameters of the proposed antenna. Directivity is 8.92, right? You can see here directivity, E-plane directivity, H-plane directivity. It is touching this 5 to 10. So it is a 8.92, right? Gain is 6.6. Reflection coefficient is minus 43.48. Then main lobe direction is 52 degree. Then side lobe level is minus 11.8. Then half power beam width is 53.9. Then efficiency is 60%. This is a very good amount of the efficiency we are getting. Then polarization is linear, right? And front to back ratio is 20.77, right? So E plane and H plane pattern for 5G antenna, and these are the performance parameter of the proposed circular microstrip patch antenna. Clear? Now our fabrication start from this point actually. These are the machine where we have fabricated the antenna. This is a dielectric curing machine, micro oven. Okay, because what happens, the way you have a dielectric sheet, then you have to clean it with the water and etc. chemical, and after cleaning you want to dry it, so you require the micro oven, right? Then negative film maker you require, because antenna pattern you have to develop on the dielectric sheets, so it's initially it has to be taken on the transparency, and from the positive to negative you have to you require machine. So this is a negative film maker, right? Dry film developer. After antenna has been printed on the dielectric sheet, you have to develop it. So you require the developer, right? Two-in-one unit developer stripper. Then this is the double-sided ultraviolet exposure unit with vacuum. Before developing, you require to expose it through the ultraviolet, right? So this is the certain procedure is there actually, right? So this is the machine which you require. Then dry film laminator, because this is the lamination machine, because these are the films, and dielectric sheet we have to insert in this machine, so the film comes on the dielectric sheet, and then you have to go for developing the film, right? Then after that you have to etch out material. After having the print of the antenna on the dielectric sheet, require etching out, right? So this is a spray etching machine, right? So this machine is required, which we have. Now drill machine is required because you have to feed, suppose antenna, you have to feed coaxially, then you require to drill it. So these are the dielectric, this is the dielectric drill machine, right? So these are the layouts which we have developed. We have designed and developed 4 antennas, right, in laboratory for different dimensions or radius. One is a 2.71, second one is a 2.4, and third one is 2.3, and this is 1.5. So the 4 antenna we have designed and fabricated. Okay, so these are the layout on transparency. These are the print on the dielectric sheet, 4.4 epoxy glass, and these are the antennas which we finally we got. You can see here, these are the prototype of CPA at 26 gigahertz. This is our antenna which we can utilize for our 5G communication application, right? The dimension, for dimension I kept scale over here. Right, and these 4 antennas you can see here we developed and fabricated, right? Is it, I think, good to see. This is our anechoic chamber for antenna testing, right? The beauty of this chamber is the software which you require for measuring the parameters we have developed in-house. Full software we have developed, because what is happening is our software was crashed due to in the computer, right? Computer was crashed, so software was not available, no backup copy. Vendor was not ready to supply. He wanted money, 5 lakh, 6 lakh rupees. So we thought, let us develop the full software at our own end, right? So we developed it. So anechoic chamber for antenna testing, and this is the gain measurement can be done. So this is a standard horn antenna, right, which we discussed earlier. The radiation pattern, of course, it is a linearly polarized, right? This is a linearly polarized, means vertical polarized. This is not horizontal, because ridge is there in vertical direction. So it is a vertically linearly polarized. And this is the positioner, where you can see the antenna is kept over here, right? And this positioner is moving in 2 directional. One is a horizontal direction and second one is vertical direction. Horizontal direction gives you the H plane, and vertical direction, if you rotate it, gives you the E plane. So the gain measurement can be done. And this is standard horn antenna whose parameters are with us. The gain is available. The cable losses are also there, which we are having. We have calculated the cable loss. Okay. And we have a vector network analyzer. And there is a fringe field equation. Now question is, how does it work actually? What is the fundamental of anechoic chamber for gain measurement? So it is based on the Freeze transmission equation, right? So it is a PR upon PT equal to this efficiency, reflection coefficient, transmitter end pe, receiver end pe, then lambda upon 4 pi r square, then directivity, then polarization factor. If both antennas are perfectly polarized, then this is going to be nullified. And if there is a complete match at this end and this end, then this factor is going to be nullified. So, and this multiplied by directivity is the gain. So finally, you are getting PR upon PT equal to lambda upon 4 pi r ka whole square GT GR. Since you have a transmitting side standard gain antenna, whose gain you know, because we have a sufficient data supplied by the vendor, right? Transmitter power which we are supplying to this antenna, we are knowing because VNA vendor has supplied this data. PR is the received power at other port of the VNA. So that VNA is calculating how much power is coming. Actually, what is happening? VNA is transmitting the power is coming to this cable, so some loss will take place, and the reduced power will come to this antenna. This antenna will radiate, so gain will get added into that, and added gain signal will come in the free space. This distance is between these two antennas 3.25 meter. So some losses will take place. That is to be represented by 4 pi r upon lambda. That is called the path loss, right? So lambda can be calculated by frequency. Let us say our antenna is working at 30 gigahertz. So according to the 30 gigahertz, you can find out lambda, and distance is constant. So you can find out the path loss, right? So after this signal is coming here, then gain of this antenna is adding to the signal, right? So signal is coming after this antenna and going to the through the cable to the second port of the VNA, right? So finally, received power can be calculated, measured by the VNA. So you are having PR, you are having PT, you are having lambda, you are having R, you are having GT. So you can find out GR. That is the receiver antenna gain. Is it clear to everybody? Now we have developed the software, as I told you, that is LabVIEW based automated software. We can rotate this in 2 dimension. So here you can write the angle, initially 0 degree, then a step size, let us say 1 degree, 2 degree, or 5 degree, or 10 degree, and maximum angle is 360 degree, right? So you can set you want H plane or E plane. You can set you want 3D plot or 2D plot, right? If you want to go for 2D plot and E plane, then you have to set the reading over here. Initial angle is 0, and the final angle is 180, because it is not 360 degree. You cannot rotate vertically this 360 degree. So it is 0 to 180, right? And the step size can be a 1 degree, 2 degree, or 5 degree, or 10 degree. Anything you can decide, right? And this is the LabVIEW based software which we have developed, right? We are going for patent, so I'm not going to show you full detail, right? But some glimpse I wanted to show you, all of you. So this software we developed at our own end, and after development, this company offered us job. Company has offered us job. Our students, they are saying send 2 students who knows the LabVIEW, right? This is VNA S parameter block code that is in the front panel. VNA S parameter front panel, right? Here you can set initial frequency, stop
Chandramohan sir,
frequency.
can you please mute your mic? Hello, Chandramohan sir.
Yes, sir, you can continue.
Okay, so right. So these softwares we developed at our own end. Some glimpse I wanted to show you, all of you. Here you can set initial frequency and frequency. Then you can set S parameter. What do you want to measure? S11, S12, 21. Because gain, ultimately everything is depending on S parameter. All the parameters you want to test through this chamber, through this concept, freeze transmission equation, you require S parameter only. S11, S12, S21, S22, right? So this here, in-house activity, I would like to tell to all of you what we are going to do is we are running one chapter, that is ATMS, Antenna Test and Measurement Society chapter. We are Central India's chapter. We are running it at in-house. Okay, in that every month, in one Saturday, we are conducting the lecture. So there nearly 35 lectures are over. Nearly 3 year are going to be over. Right. So we are also going for NABL for our this laboratory, right? So this is the quality manual first page I would like to show to all of you. And these are the list of the parameter which we can measure from this anechoic chamber, and through the software which we developed our own at our own in-house. So gain can be measured, directivity can be measured. This is a polar and 2D directivity we can measure. Then efficiency we can measure. E-plane radiation pattern we can measure. H-plane polar radiation pattern we can measure. E-plane 2D XY radiation pattern we can measure. H-plane 2D XY radiation pattern we can measure. Axial ratio with 2D and polar we can measure. 3D radiation pattern we can measure. SAR, that is a specific absorption rate, we can measure. Reflection coefficient of the antenna we can measure. Return loss we can measure. VSWR we can measure. Smith impedance plot we can measure. 2 and 4 port MIMO parameter we can measure. Then cable loss we can measure. So these are the parameters. Earlier we had 4 or 5 parameters only, but after developing software at our own end, we are able to enhance our capabilities. So now 16 parameter we can measure. These are the current activity. SAR measurement we have done just 2 days back. So a particular person who had some project from MESE, he told, sir, we want to measure the SAR. So we provided this facility. So this is he wanted to measure the permittivity of the material. So we provided this setup, coaxial waveguide setup, right? Through the VNA, we found the S11, 21, 22, 22, 21, and putting some equations and algorithm and developing some MATLAB codes, we found the dielectric constant of the phantom, that is the nearly 50, right? Because he is using the phantom for SAR measurement. So a very small antenna he have kept below the phantom, right? You can see here this VNA other port, the cable is connected, which is going to the antenna downside, and on the antenna water has been kept, and on the water he has kept the phantom equivalent, that is the gelatin material, cubic you can say structure, okay, that is equivalent to that. And here from the top we have found the different value of the electric field and different location, and we found the SAR value of this particular antenna, right? So now conclusions. Planar technology we discussed, the parametric analysis we have done in CST, then antenna has been designed and simulated, right? Then uh, then we have antenna is tested experimentally using vector network analyzer, right? So many parameters we gone through, like side lobe label, main lobe directions, efficiency, etc. Then we have proved and we have developed the antenna for 26 gigahertz, that is for 5G applications. Okay, so these are the references. And acknowledgement. I would like to acknowledge. I would like to thanks to Ministry of Human Resources and Development. I would like to thank to ICT New Delhi, and I would also like to thank to SGSITS Indore for providing TechU funded research facility to accomplish this proposed work. So thank you all. Thank you so much.
Thank you, sir. Thank you, sir, for
Thank
your
you.
insightful and excellent session with the realistic simulated values. Sir, there are
Yes.
few questions from
Yes,
the
definitely.
participants. Yes. Suggest optimum feeding network method for broadband circularly polarized antenna arrays in band. This is a question.
Optimum
Optimum feeding network method for broadband circularly polarized antenna arrays in band.
amendment. Okay, so what is the problem in that? Optimum feeding network means what? Matlab, you want to
Sir,
ask a network analyzer?
Arun sir is asking this question. He is asking,
Sir, I'm
please.
audible, sir.
Yeah, you are audible. Please ask. Will you clarify a little bit this question a little bit?
Yes, sir. Actually, sir, I want to design an antenna array, okay, which is a broadband,
Okay.
which starts from 10 gigahertz to 40 gigahertz.
Okay.
Specifically, I want to use this circularly polarized antenna, left hand and
Okay.
right hand circularly
Okay.
polarized
Right.
antenna.
Right.
It is okay. So I want to know that whether I can go for corporate feed or substrate integrated waveguide method, so that in order to avoid the losses and the phase errors.
You see, I suggest you, if you're doing the research, you can go both you can opt both. You try both and compare and validate the results. I shall tell you. Yeah, you know the two approach. One is the corporate, and second one is this subtrade integrated waveguide. Okay, so
Yes, sir.
your amount of work will increase. That will boost up your confidence and create a lot of knowledge in you. Okay, so
Yes,
don't
sir.
try to get the shortcut. If any question is coming in your mind, then you implement yourself. You check up, right? Which one is better? So you prove it. Doing both of them, implement both of them. This is
Sir,
my suggestion.
yes, sir. That I can try, sir. And sir, one more thing.
Yeah.
This precise fabrication in India, any vendors are there?
There are a number of vendors. Actually, machines are very costly. It depends on your budget.
Yes, sir.
Like etching machine is there. So etching you can do dry etching or wet etching. है ना? And some are dry etching machine. They are costly 50 lakh or 60 lakh rupees. So it depends. If you spend money, you will get the quality machines. So your work will get improved. There are a number of vendors. If you Google it, you will find it.
Okay, sir. I will see, sir. Ha, sir. Thank
Okay,
you, sir.
you can check up. And my contact number is there. Any help you require, I can do it.
Sure, sir. Sure. Ha. Thank you, sir.
Sir, next question is from Hina madam. She is
Ji.
asking what is the wavelength for mmWave and what is the desired beam width for mmWave?
Desired beam width.
Yes.
Yeah, I have listed in my this. You can see here. Desired beam width. It depends on application to application. Right now, what I'm going to say is right now the vendors are shifting. Companies are shifting from 4G to 5G. Right? Is it clear to all of you? They fully 5G has been not implemented in India. So it depends. Beam width depends on the location. In the south, there may be a different beam width antenna required. In MP, if it is central India, then the different beam width antenna may be required. So it depends on region to region, right? I have developed my antenna for this particular bandwidth. That is, I will show you my beam width, half power beam width. It's a 53.9 degree. Right? Because our Indore is very much crowded actually. And moreover, the Reliance has set up their own tower nearby my institute also, just on the road, a 5G tower, though they have not started using it so far. So just by discussion, we came to know that they require the large band beam width antenna. So we got the 60 degree. It is enough, I think.
Okay, sir. Any other queries from the participants? Yes, Hina madam. Yes, Hina
Hina
madam.
madam, you can unmute.
Ma'am,
Yeah.
yeah. Ma'am, I just wanted to ask, is there any mathematical model available for the calculation of these many things?
Yes, yes. You see, for conventional prototype, there are equations available, like rectangle patch antenna equations are available, mathematical derivation is available. You can see the 14th chapter of C.A. Balani, antenna theory and analysis. Lot of conceptual things are there. Lot of equations are available. Lot of theory is there. A lot of derivations. You can have a lot of idea. But for conventional microstrip patch antenna like rectangle or circular or other shape, just a regular shape, derivations are available, relationships are available. But suppose you have a complex geometry. Suppose you have a multiple patch antenna, you have a stack patch antenna, or you have a E-shape patch antenna. But for that, you may not have a derivation or equation which can relate the parameter with the resonant frequency or bandwidth. Then these equations you have to develop yourself by your research work. You can apply the soft computing technique or some other curve fitting methods are there by which you can develop the equations and then you can use them. Is it clear? My answer is clear to all of you.
Yes, sir. Thank you, sir.
Yes.
Okay.
Any other queries from the participants?
Any question? I'll be happy to answer it.
Okay.
Attendance is very good, 120,
There's only
126.
one question, sir. This is Dr. Vikas Gupta from VSET.
Okay.
Vasai. I am also from Ujjain, passed out from GC Ujjain. I know Chopra sir and all
Okay.
that.
Okay. Great.
IEEE.
Great. Nice to see you.
Yes. Sir, some research my student is doing in the UWB antennas.
Ultra
So,
wideband.
yeah,
Okay.
these rectangular strip antennas.
Mhm.
So, which simulation method may be better? Because some simulation method are showing some results which are good in simulation, but when we practically do it, we are not getting desired results.
You see,
Yeah.
you see, it is. I shall tell you the root cause actually.
Yes, sir.
Uh, you see, all the softwares are very costly. HFSS is there, which is well accepted internationally.
Mm-hmm.
CST is available there, right? I3D is there. All three are accepted there. If you work them, all are accepted for publication, etc. In all international conferences, journals. You know, it depends. Suppose you have a CST, then you are bound to
We are
use
doing on
CST.
CST. We got to tie up
CST.
with BITS,
See,
Bilani,
I
Hyderabad.
suggest you,
Yeah.
I suggest you to
Yes, sir.
go through with that only. For simple, this ultra wideband antenna, CST is enough, sufficient, no
Okay, sir.
problem at all. But if somebody says CST is not good, then you cannot go for I3D or HFSS because there is a license issue nowadays. So no
Okay, sir.
lab can have all three. There is a fund issue in microwaves everywhere, almost in engineering institutes at least.
Yes, sir.
Right. So if you have a CST, you can do it, no problem at all. CST is a well accepted and very easy to use it. It is user friendly.
Yes, sir. Yes, sir. Thank you, sir.
Thank you so much, sir. Sir, we
Okay.
will have a photo. So I request all the participants to switch on their cameras for 2 minutes.
Okay. Right.
Share your screen. Yeah.
But my background is not that much good,
That's
and I'm
okay,
simply.
sir.
No problem. It's okay.
It's okay. But anyway, I do something.
It is okay, sir. No problem.
Yeah.
Photo team, please let us know once it is done.
I think I'm just in time. I think I finished this 7:30
Yes, sir. Yes, sir. It is
because there
within.
was a clear cut instruction from the Ranjanwala madam that sir don't be particular in this time. So I was very particular about it.
Sorry
Yes.
to disturb. Will you please stop sharing your screen?
Yeah, okay. I'm going to stop it. Right.
Yes, it's done. Thank you, everybody.
You all.
Thank you so much.
Sir,
Thank you.
there is one question from Snehal, madam.
Yeah, please.
Can we download CST software?
You can download CST software for student version only for limited time period.
Okay.
Unofficially, so many things I can tell, but this will be recorded, so I won't tell anything much beyond that. You understand it. But I suggest you CST is easier, cheaper. In 4 lakh you can have a CST and perpetual license. Right, we are using CST license copy. We are using because in publications license software must be mentioned. Right, so that is the thing. CST student version is available. You can ask your student to download it from the website. You can use it for certain period, demo version, and small applications are possible with that actually.
Sir, one more question is there. Can we use this microwave applications in medical imaging or medical imaging? Can
Yes,
we?
definitely. Imaging, microwave imaging is what? Micro imaging is some sort of transmission of the signal, and you have to receive from other side, etc. So you can do it. SAR measurement you are doing. SAR
Okay.
measurement is what? Measurement is a biomedical application.
Okay.
So you can do
So
it.
it is.
All simulators are ocean actually. There are so many packages. We are working just basic work, designing antenna, designing antenna. But there are n number of things can be done by any software.
Okay, sir. Okay, thank you. Thank you.
And moreover, you can develop your own code. MATLAB codes you can use. We have published one paper. We have not used simulator. We have developed our own method of movement codes using the MATLAB, and we have created all the plots like gain, directivity, efficiency, excel ratio, etc. CST is what? Vendor is supplying
So,
you CST.
CST or MATLAB, sir?
The
Which one?
MATLAB,
And
then
CST or MATLAB? Which
CST,
one is
all
more
simulator
preferable?
like CST, I3D, HFSS, thीज ऑल सॉफ्टवेयर, ये जो सारे सॉफ्टवेयर हैं, ये
Yes,
सारे
sir.
सॉफ्टवेयर सिमुलेटर हैं और ये बेबी वर्क करते हैं एक प्रकार से। आपने इनपुट दे दिया, वो आउटपुट बना के देगा, 10 मिनट में एंटीना डिजाइन हो गया, है ना?
Okay.
दैट इज नॉट
Yes.
ए रिसर्च एक्चुअली।
Yes, sir.
यू मस्ट नो व्हाट इज हैपनिंग बैकग्राउंड, है ना? और यू डेवलप योर ओन कोड्स, मैटलैब कोड्स आप डालिए, डेवलप कीजिए अपने खुद के। 3D पैटर्न कैसे करते हैं, इवन सिंपल डायपोल का ही आप कोड लिख के बता दीजिए, लिख दीजिए,
Okay. Okay, sir. Okay.
है ना?
Thank
सो
you.
इट
Dr.
इज
Rasika, I guess we should wind up because next speaker is also joined.
Okay, okay, madam.
okay.
Uh,
Okay, right.
yeah,
Thank you
Satish.
so much.
Thank you so much, Satish sir. It was great
Okay,
connecting with you. Thank
Yes,
you.
sir.
okay. Thank you. Nice to meet all of you on screen.
Thank
I'm
you, sir.
I'm happy. Thank you so
Yeah.
much.
Thank you so much, sir.
Thank you.
Okay. Moving ahead to the next session of Day 2 Atal FDP on mmWave technologies. Our speaker, Dr. Gaurav Chaitanya. It is my pleasure to introduce our speaker of the day. Dr. Gaurav Chaitanya is an experienced faculty, researcher, mentor, and trainer with a demonstrated history of working in the higher education industry with strong education professional and research background focused in RF and microwave engineering. His research interest includes frequency selective surfaces, 3D printing, metamaterial, and absorber design. He has completed his PhD degree from Indian Institute of Information Technology, Nagpur, and ME degree in Electronics and Communication Engineering from IES IPS Academy, Indore. He is currently working as an associate professor in the Department of Electronics and Communication Engineering at the Acropolis Institute of Technology and Research, Indore, MP. He serves as group head of the innovation cell under the Acropolis Innovation and Incubation Hub Foundation. He has published over 50 research papers in referred journals and conferences. Additionally, he is the faculty coordinator of the AICT Idea Lab. He is skilled in entrepreneurship education, design thinking, innovation management, critical thinking, intellectual property rights, and incubation management. He is nominated as Innovation Ambassador by Ministry of Education Innovation Cell. He is mentor and global jury member at Wadhwani Foundation National Entrepreneurship Network. In addition, he is very active in the national and international arena with leadership positions in professional organizations such as IEEE, IST, and IAER. He is senior member of IEEE and life member of ISTE. We are honored to have such an esteemed personality with us to deliver this session on mmWave and microwave frequency selective surface based absorber. We on behalf of Department of Electronics and Telecommunication Engineering, Vivekanand Education Society's Institute of Technology, and from all participants from various states, we welcome you, sir, in today's session of Atal FDP. Thank you, sir, for taking time to be with us. Now, I request, sir, to conduct the session. Over to you, sir. Gaurav,
Thank,
sir.
thank you so much, Rasika madam, for this warm introduction. Uh,
Yes.
Let me just share my screen so that it's visible or not. Just let me know.
Yes, sir.
I hope it is visible.
Yes, sir, it is visible.
Yeah, the screen is visible. Can I start?
Yes, sir. Yes, sir, it is visible. You can start.
Thank you so much. So I'm here to present my talk on frequency selective surfaces based microwave and millimeter wave absorbers. Very good evening to one and all present. So let us understand what are frequency selective surfaces very first. So they are the periodic unit cell arrangements which are having the element type of patches and slots type of arrangements, and which are performing the frequency filtering for the incident electromagnetic waves which are impinging towards it. They are selectively reflecting, either transmitting or absorbing the electromagnetic waves, and it certainly depends on several things. That is the shape of the FSS, the size, the element spacing, and the orientation of the incident wave. Now you can see here there are two types of arrangements that I could show here: a patch type of resonator and a slot type of resonator. Here there is a patch type of resonator there where you can see there are some metallic rings which are been there on the top layer of the substrate. And if we find out the equivalent circuit for this, the equivalent circuit will be almost equivalent to the series ILC circuit, which will contribute towards a band stop type of filtering network. And the complementary to this type of arrangement is this slot type of arrangement, where you can see a loop has been edged out from the metallic part, and then what we can see here, it is going to give you a parallel type of arrangement, parallel LC network, which contributes towards the band pass type of responses. So if we see the applications of FSS, there are a wide variety of application in FSS at present. They are very well accepted in radomes, absorbers, antennas, polarizers, spatial filters, EMI shielding, dichroic subreflectors, high impedance surfaces. So out of this, if we talk about the absorbers, in today's interconnected world where industries rely heavily on seamless communication, the management of electromagnetic waves is paramount. Across sectors such as telecommunications, aerospaces, radar systems, anechoic chambers, the demand of efficient electromagnetic wave control mechanisms has intensified. At the heart of this demand lies the crucial role of microwave absorbers. Microwave absorbers find extensive industrial and practical application. In telecommunication, they are certainly crucial for reducing the interference and enhancing signal clarity in antenna systems and satellite communication. In aerospace and defense, microwave absorbers play a pivotal role in stealth technology, aiding in reducing radar cross section of military assets and calibrating radar systems for accurate measurements. In medical imaging, if we can see, the microwave absorbers improve image quality and reduce electromagnetic interference in techniques like MRI, magnetic resonance imaging. Additionally, they facilitate the material testing and testing processes, ensuring accurate measurement and analysis. If anechoic chambers we talk about, they have been utilized for electromagnetic compatibility testing and antenna pattern measurement. One of the finest application is EMI reduction. Even in the automotive industry, if we talk about energy harvesting, or in the microwave absorbers are employed in to reduce the interference and improve signal integrity in vehicle designs, the electronic vehicle designs, contributing to the development of advanced driver assisted systems or autonomous vehicles, if we can say. If we see the physics behind how a microwave or millimeter wave absorption takes place, so generally a microwave or millimeter wave absorber exhibits the absorption at microwave or millimeter wave frequencies, and they will certainly go for a single or a multi-band absorber. How does it taking place? So if some electromagnetic energy, which is, if in this case, if I talk about it, it is going to be EI, it is impinging on the absorber surface. Either it will transmit or it will reflect back. So to get it as an absorber, we need to certainly minimize the transmitted power as well as the reflected power simultaneously, which is coming out through this particular equation, where absorptivity will be equivalent to 1 minus S11 square minus S21 square. Now, how this can be done? So one particular solution is we are applying a ground plane on the other side of the absorber. So that this complete metal lamination, how it is ensuring, it is certainly giving a zero transmission. So there will be no transmission in this particular case, only there will be a reflection. Now, so this equation will now be reduced to A is equal to 1 minus S11 square, as S21 is now been equivalent to 0. How to get the reflection or minimize the reflection to be 0? So here we can using the impedance matching criteria. We can design it as such that the input impedance is matched exactly with the free space impedance with this particular formula. So microwave or millimeter wave absorbers finally uses frequency selective surfaces as one of the major tasking for getting this particular impedance matching criteria to be fulfilled. So if you go for the traditional absorber, there are certain challenges which are associated. If you talk about Salisbury screen or a Jaumin layer, a Dellenbeck layer, or a pyramidal absorber, or the materialistic absorbers like ferrite, where people are using graphene, carbon nanotubes. No, they do have certainly challenges associated, like most of them are very expensive, they are bulky, cannot be transported, they are fragile, very thick. So certainly when the real time applications are coming into picture, such type of things are certainly been not into much in demand. They are certainly been traditional, but there are few very better solutions nowadays into the market. So the advancement towards this traditional absorbers are the FSS based absorber designs, which is coming with the benefits of reduced bulkiness. It do have an enhanced and the strong absorption as compared to the previous traditional absorbers. Then I do have an ultra thin geometry of the order of almost lambda by 20 as the unit cell size. The design is scalable, where you can scale out the design from a very low frequency to a very high frequency, so microwave up to a millimeter, then to a visible range as well. It do have a high angular stability and coming up with a cheaper cost. The popular fabrication method for such type of absorbers is photolithography based PCB manufacturing process. Let me make you understand the measurement technique, because recently Dr. S.K. Jain was there, and then he introduced you to several particular good measurement techniques for measuring the antennas. Here I am giving you the measurement techniques, how to analyze or how to finally find out the parameters for the absorbers. So here this is the setup what we are using for the absorber design measurement, where two antennas are placed in the near proximity of each other, and then the background noise has been recorded. Now we are keeping a metal plate at the front of the antennas, and the transmitted power has been measured, which is S21 square. The metal plate then can be replaced by the fabricated sample, whatever we are fabricating with the identical dimensions. We are generally making a dimension of almost 250 cross 250 mm or 300 cross 300 mm, generally passive in nature. And then the transmitted power of the fabricated sample has been recorded, and the transmitted power from the copper plate has been subtracted from the fabricated sample, which generally gives you the actual measurement. So this is how we are going for the normal incidence measurement technique. Now if we go for the oblique incidence measurement, so we do have two types of measurement technique for this, where we do have measurement done on the different polarization angles and the normal incidence, and then for different oblique incidence angle. So if we are sending the wave normally, like this, with a zero angle between, and keeping the transmitter and the receiving antenna in the close proximity, what we can do is we can rotate the fabricated structure over several angles with some step sizes from 0 to 45 up to 90 degree, and then we can see whether if it is going to be a 4-fold symmetry or a 6-fold symmetry structure. Generally the structure gives you a polarization free or polarization insensitive response, and that is the requirement, that because the real time applications, we generally don't get all the incident waves to be only impinging towards from the normal. It generally comes up with an angle. So such type of arrangement is necessary, and such type of calculations are also necessary to generally calculate the response of the absorbers. Another particular thing is the oblique incidence under TE and TM measurement. What we can do is, now we are keeping the sample as the fixed place, and then we are generally increasing the angle between the transmitter and the receiver from 0 degree to 90 degree, and then we used to see that up to what degree of TE polarization or under TM polarization, generally we are getting a good response. So we call that response as the polarization insensitive behavior or the polarization stable behavior of the fabricated absorber. So if we go for a narrowband absorber, certainly in 2006 itself, the split ring resonator has been designed. A frequency selective surface based metamaterial absorber it do have, which illustrates the proposed absorber with narrowband characteristic, which it comprises of certainly an array of split ring resonators. You can see this is a split ring resonators arranged perpendicular to this resistive sheet, and they are arranged in such a fashion that the resistive sheet, which is almost having a 1 thickness with an impedance of 377 ohms, which functions akin to a conventional Salisbury screen. The incident magnetic field aligns perpendicular to the plane of the split ring resonators, inducing the magnetic excitation in the resonance in the ring. However, this proposed absorber, if we can see, it do have some resonance at almost 2.0 gigahertz of the frequency and having a non-linear structure. Such type of arrangement are difficult to transport or to arrange it at the same fashion with all the angles. So then comes up with an structure given by Landy. He is given the first metamaterial based absorber realized by him with a structure size of almost lambda by 20 as compared to the conventional absorbers. Of course, these absorbers are scalable from microhertz to terahertz, terahertz to infrared, infrared to optical. Now, they can be easily fabricated, as I already told you, with the PCB technology. He introduced an alternative method, certainly, for the narrowband absorber, addressing the limitation of the prior design. You can see that there is going to be some electric resonator, ring resonator has been introduced on the front, and then there is an patch plate which is been there at the bottom. However, we can see this is a partial ground, not a full ground, and that's why there is a need to minimize both the transmitting as well as the reflecting power, and they are getting almost 96% of the absorption in this particular case. Here, let me show you how this absorber is certainly been working out in a single band absorber method. So what we can see, there is a resonating ring here on the top of a dielectric substrate. Generally, a dielectric substrate that has been commonly used is 4.4 epsilon R and 10 delta 0.02 based FR4 lossy FR4 material. And depending upon the size of the unit cell and the dimension of this particular ring, we are getting a resonance at almost at 5.05 gigahertz with absorptivity of 99.54. Now, how we are getting it out? If you see the surface current distribution, what we can see that the distribution of this, you can see this array or the array of the arrows, they are in the direction of the incident wave. So on the top surface, they are generally in this particular direction. If you see the bottom surface, they are in the opposite direction. So they are making a loop type of structure, certainly ensuring the absorption behavior. A magnetic type of loop has been formed out here. Now, why this absorption is taking place? So there is one study given out here. What we can see here, this is the equivalent circuit for this ring resonator, where this R and L is going to be the inductance of this ring. R is the associated resistance with this inductance, and then we do have because of this gap in between, we do have this capacitance here, and then there is a dielectric D because of the between the full laminated ground plane and of the top plane. So this is going to be the D. Now the absorption takes place because of two things. Certainly there are ohmic losses which are associated and the dielectric losses which are associated. So this study generally gives you that because of the ohmic losses, that is generally because of this top copper ring. So if we see this with a lossy dielectric losses because of the dielectric material in between, we can see that it is going to give you a very good reflection coefficient of almost minus 20 dB and giving a good absorption at almost of 5.02 gigahertz. Now, if we replace this copper, which is having a finite conductivity with a perfect electric conductor and having a lossy dielectric, what we can see, there is a very significantly very small deviation in the reflection coefficient, but that is reducing from minus 20 to minus 15. So we shows that this ohmic loss because of this this ohmic loss, because of the top this top ring is certainly been contributing very less as compared to the dielectric loss, which is the main contributor towards this particular absorption which is taking place. Now we can see that if we are going for a copper again with a finite conductivity with a lossless dielectric, and with the same particular density with a perfect electric conductor in the lossless dielectric, what we can see, it has been reduced to significantly to some minimal of -5 dB, which is very small value. So this proves out that the dielectric losses is the main contributor, and how much we go with this particular type of losses. So we can see that it is, if we go with a 10 delta value, from 0.002 up to 2, what we can see at 0.02 we are getting a significantly good value, and then if we are increasing it further, it is again reducing. So reflection tips improves linearly with that of the 10 delta. So increasing the losses more will also not contribute. At a particular time you need to stop, and then it is going to be an optimum value. Now from one particular ring, if we introduce two rings, what will happen? We'll get two resonance, obviously. So we are getting a resonance here of -23.11 dB at 4.95 gigahertz and -36.54 dB at 10.24 gigahertz. And what we can see is we are getting two resonances because of the ring 1 and because of the ring 2. The similar type of arrangement is again going to be here. Again, what we can do is we are also going to use some particular multi-resonating structures where we are using a PET substrate here, and then we are having some quarter part of the annular rings at the ends, one particular ring with another thickness, another particular ring with a different thickness, and then the cyclo structure, a cyclo square structure in the center. What we can see is here, because of this structure 1, we do have one particular resonance. Because of this structure 2, we are giving another particular resonance, which is the smaller at the lower frequency side, and because of the structure C, we are getting another resonance, which is at the this particular middle part. So we are getting three resonances at 6.01, 9.55, and 11.65, with having different resonances at C and X band, with the full width hat maximum, where what we are calculating this full width hat maximum generally at the 50% of absorptivity. So we are getting for 6.01, it is 158.5 megahertz, 261.6 megahertz, and 296.1 megahertz, which are generally significantly giving a narrow band response with three different bands into the C and X band. We see at the millimeter wave, the similar type of arrangement. What we can see is, because of this split ring resonator structure, one resonance we are getting at 77 gigahertz, and another one, which is because of this inner type of particular structure, we are getting at 110 type of 110 gigahertz as the resonant frequency. So such type of arrangement has been somewhere done by PK Singh here, where they are using a polyimide as the substrate, and then the gold as the metal ring, as gold metal has been realized with the metallic part. So this has been shown here. Then if we are going to bring the resonances close enough, we can enhance the bandwidth. So what we can see here is, because of this outer split ring resonator, we are getting one response, that is this one, and when we are getting some meandering line of arrangement here within inside, we are getting another response. Now we are trying to bring this particular responses so close enough to each other that they contribute together in a enhanced response with a significant full width half maximum bandwidth. Okay, and then we can see that this is the fabricated part by PK Singh, and this wonderful flexible part we can see here, where it can be very well bent with a different radius of curvatures. However, the complete assembly is very costly because we are using gold as the metallic part and the polyimide as the substrate. But although such type of arrangement are very well versed here, and they are regularly used in the industry. Another type of thing what we can use is the bandwidth enhanced, to get the enhancement in the bandwidth is again bringing the resonators close enough in order to get the resonances. So here is another particular design. You can see here we do have three resonances at three different frequencies. When brought close enough to each other, they not only they brought a bandwidth which is broader enough to 1.48 gigahertz, significantly very broad, and not only that, but they also shift, so they red shift towards the higher side, where we are getting the resonances now at different frequencies than the original resonances. So because of the coupling effect of these three resonators that we have been using here, resonator X, Y, and Z, we're getting a bandwidth enhanced response. So this is the experimental verification for the same, and we get a very good agreement between the simulated and the measured part. There is another particular approach for the bandwidth enhanced FSS based absorber, that we can go for a multi-layer approach. So if you go for a multi-layer approach, it is featuring a model's accuracy and scrutinizing the numerical simulations, aligning closely with analytical calculation for layer counts up to 40 as total, where we are using the metal and dielectric type of arrangement, stacking type of arrangement, and leveraging this model, the proposed method has broadened the absorption bandwidth, either by increasing the layer count or by arranging the unit cells in a close proximity. So simulation affirms the efficacy of this approach, showcasing that a 40 layer configuration achieves a near ideal absorption at almost 0.96, that is from 0.4 to 1 terahertz type of arrangement. We can see that for almost a count of 1 functional layer, we are getting this as the bandwidth. For 10 functional layer, the bandwidth increases further, and for the 40 layers, the bandwidth even increases further. So a bandwidth enhance can be certainly we can get it from a multi-layer type of structure like this. We go for a millimeter wave type of arrangement. So again, it has been there. We are using a stacking with these three different resonating structures, where we are getting one end we are getting a loop, another is the cruciform type of structure, and another thing is patch, which are certainly been giving resonances at 3 different frequencies. But when stacked together one another with some particular type of dielectric filling in between them, maybe air or foam, what we are getting, if this author has done what he has done, he has actually calculated the combination of this two, and this two, and then he come up with that these two combinations gives an optimally higher bandwidth, the ultra wide bandwidth from 6.3 to 40 gigahertz with 10 dB bandwidth here. So this type of arrangements again come with a multi-layer structure. But there was some, you can see there are some grating lobes which are associated here, and these grating lobes are been not very well versed. This problem has been solved by introducing this spiral type of arrangement at the first unit cell, and then which is followed by again a loop and the patch which is packed with a copper metal. So this is the fabricated part, which has been fabricated using the carbon black ink, and they are stacked together, and we are getting the response, which is ultra wideband response in the absorber. Another particular method to get the bandwidth enhanced response is the inclusion of air spacing or the lumped elements. So what we can see here, certainly this is one particular type of resonator that has been designed, and then there are some resistors which has been added on this particular junctions of almost 100 ohm. Now, because of this particular thing, if you can see the second absorber response, this is the response they are getting. They are optimally not that wide. They introduced some type of air spacing in between, and then increased it further. What they can see is they are getting a very well versed response with almost an ultra wide band response from 3 to 12 gigahertz. So there are certainly, for bandwidth enhancement, there are certainly another type of circuit analog absorbers are there, which are generally realized and will widely researched by the peers. So the dielectric thickness should be very large enough to realize this type of resonances. The resistive as well as the conductive part here present.
Hello, Vivek sir. Hello, Vivek sir. Can you please mute yourself? Okay. Yes, sir. You can continue. Sorry.
Yeah. So certainly in this type of circuit analog absorbers, what we can see here, either we can realize it using the lumped resistors, or the resistive ink, or the resistive paint. So such type of arrangements has been generally been realized and studied by the peers in the last decade. So what we can see, if we are using the lumped resistors, they are certainly low cost, but putting the resistors in such a small geometry, and then ensuring that every particular resistor is very well soldered well, which it's a time consuming task. So the another particular thing is a resistive ink method. The accuracy increases, but the cost also increases a lot, because such type of arrangement requires micro machining type of facility for fabricating it out. Certainly, it is there in IIT Bombay, IIT Kanpur, IIT Kharagpur, but requires a heavy amount to be associated with it. So the funded projects can go for this, but generally, a researcher with no fund in hand could not use this resistive ink type of arrangement. Then there is another particular arrangement where resistive paints are used, where the cost is average and the accuracy is moderate. Although we also used this type of resistive paints. This is a carbon black paint. Another type of resistive paint which is very popular is the silver paint. So almost a bottle of 100 grams comes with 9,000 or 8,000 rupees, and we come up with almost 3 to 4 prototypes with that, which is optimally good for us for fabrication, and we are getting a very good results out of it. So what we can see here is again going to be an annular ring type of structure with which is having a gaps in between, and the gaps are filled with a resistance of almost 150 ohms in between them. And what we can see, this type of arrangement is going to have an equivalent circuit like this, and giving you an Salisbury zone almost at the resonance of almost 11.92 gigahertz with a thickness of lambda by 4. So what we can see, we do have two types of admittance cancellance procedures here. So one is this dip, which is almost 9.39 gigahertz. We are getting a cancellation of admittance, and another is this dip, which is almost of 13.83 gigahertz. We are again getting an admittance cancellation, which is taking place, and because of this, we are getting a bandwidth enhanced response, which is not there if we are not using this type of lambda elements in between. So this is the experimental verification. Although the lump soldering is they are surface mount out here, and a small deviation if it is observed in the fabrication. So generally, the parasitic values of SMT components, and because of other tolerance of fabrication, the values sometimes deviate. Otherwise, it is widely accepted, and people are using it for fabrication of bandwidth enhanced absorbers. Another type of techniques is using resistive sheet, as I mentioned. So here what they are using a films of ITO, which is indium tin oxide, and with an air spacing on a PET type of sheet. So the beauty of this type of arrangement is they are optically transparent. So not only we are getting a bandwidth enhanced response, but they are optically transparent as well. Even we can, from a naked eye, it is very difficult to find out where is our top patch. It is out. So the indium tin oxide is again transparent. PET is transparent, and we are using air in between as a spacer. So it is optically transparent thing, which is very much useful for the canopies of aircrafts or the windows of the helicopters. So such type of arrangements are there where we're using the stealth technology, and we want a very good response of absorption. So that has been there with such type of arrangement if we are using. Another thing is broadband absorber using the resistive paint. So generally they are using the screen printing technique where we are using the squeezy for developing out of this particular top the patches of annular rings 1, 2, and 3, and such type of things they are resonating so close to each other that we are getting a bandwidth enhanced response as shown out here. But it requires fabrication procedure requires a good amount of dedication and the expertise before we go ahead. Just painting it out with a brush doesn't work many times, because if this particular thing thickens out, this resistive becomes an conductive type of arrangement, and the response completely damages out. So we have to be very much careful if we are using such type of resistive print arrangement. So that can be used on a screen printing type of technique we are using. So that becomes more prominent and the tolerance free. So another is the reconfigurable absorber. Certainly what we can see is the arrangements that I have shown till time are generally being off with a fixed frequency response. So if we want to change the frequency, we need to use another particular absorber to be designed. So such type of arrangement is very difficult when we are using in the industry or into the defense or in the military, where every time if we are getting for different frequency radars, we need to change the old arrangement. So it is better to use a reconfigurable absorber, heavily in demand nowadays. How to obtain a reconfigurable behavior? So there are several particular methods which are available into the literature nowadays. One is very popular one, that is the electronic technique, where we are including either the vector diodes or the pin diodes or the MEMS switches or the solid state devices or the biasing networks to get the reconfigurable behavior. However, this increased design is going to give you more complexity to not only to solder but also to give the biasing network. Then there's a magnetic method used. However, the characteristics here are they are very heavy to make, and then requires a large response times, so not suitable for outdoor use. Another thing is we can use for a material based approaches, generally in millimeter wave frequency based absorbers. This polymer based or the graphene based response is certainly very popular nowadays, where people are using different type of polymers as the dielectric material, and but they do have a limited commercial availability. It is very difficult to get them, what is my personal experience also. So people are also using, sometimes they are using fluids and the liquids, as the even the water has been used, the salted water or the resonating water has been used as the dielectric part. However, they do have the leakages issue to be associated with it, so we have to be very careful that there should not be any particular drop of water. Even if it is going to be an exposure with heat or maybe with the temperature changes, the dielectric constant changes, and it generally gives the different responses as with the desired responses. Another one is the mechanical method, where we can rotate or shift or fold or stretch the material or the dielectric material, and then we are getting the responses as to be changed. So let us understand them one by one. So one is the electronically reconfigurable material. So here they are divided into three, further classified into three. One is the switchable absorber or the reflector, where we can switch an absorber to a reflector and a reflector again back to an absorber. Another one are switchable absorbers from one frequency to another frequency, that we can make absorber to be switched from 1 to 2, 2 to 3, or maybe single band to dual band to triple band as well. And then we do have tunable absorber, where we can have the complete range of frequencies changing, and we can tune them on as per the desirement and the requirement. So such type of things are available. So one is when you go for the absorber or the reflector type of switchability, we do have still the technology as the application associated, where we can have its own radar during reflective state, but it can as an absorber as the complementary state. So one in particular thing, it can become a aircraft detected by its own radar, or it is going to be reflective part, we can go for an absorber. Then in the switchable absorber, which is having an application electromagnetic compatibility testing, radar camouflage and deception roles, or taking an asset tracking systems. At the similar time, when we are using for tunable absorber, they are going to use they are going to be used in a wide fashion in reduction for radar cross section reduction in redomes, and they can compensate the fabrication, the installation errors. So let us understand them one by one. One is the switchable absorber and the reflector. Now you can see this ERR type of arrangement here, where the electronic resonating ring structure has been there. And if we see the surface current distribution, this is the surface current distribution given. So we can see there is an optimally very good current which has been flowing through this central connect out here, and this has been fabricated, and we are getting a response. So we are calling it as an on state. Now, if we remove this central part where this connectivity has been removed, so what you can see, if we are putting some particular electromagnetic wave impinging on it, we can see there is no particular energy which is flowing it out. There is no electromagnetic wave or the electric current which is flowing it out. So the off state, generally it gives a reflector type of behavior. So one is we are getting a very good reflection coefficient of almost minus 25 to minus 27 dB as the reflection coefficient, and at that time we are getting a 0 dB, which is going to be a very good reflector in this case. Now, how to realize such type of arrangement into one? So what we can use here, we can even use here as a pin diode as a switch. So generally a pin diode model has been used as a switch. This is a pin diode model, where in the on state generally it goes gone for some resistive value as 3 ohms, and then we do have an off state, we are getting a capacitance of 0.1 picofarad. So we can see that in the on stage, generally it works, the central connect works like a resistance, and in the off stage, generally it works like a capacitance, and that's why the equivalent circuit changes, and that's why the behavior also changes. So in the one single arrangement, what we can get is we can realize an absorber as well as the reflector. So this is one type of arrangement that can be realized as a reconfiguration. Another thing is the switchable absorber. So what we can see here, another type of arrangement. Here again we are using the pin diode, but now it is between 2 unit cells. So you can see the pin diode has been used between 2 unit cells, not in between the patches, but also between the unit cells. Now what we can see is putting it again they are of course, the behavior remains the same. For the on state, what we can say, for the forward biasing or the on state, we can see that is going to be having the RL network. However, for the off state, is going to be an LC network. Now, how it is taking place? For the on state, what we can get is we are getting one particular frequency resonance at 4.1 gigahertz, and for off state, we are getting some frequency resonance at 4.8 gigahertz. So why this is happening? For the previous case, it was not happening. It has generally been changing from absorber to reflector and back to the absorber. But for this case, what we are seeing is that it is going to get it from one particular frequency and changing to another frequency and not going to back to a reflector this time. And this is because now you can see the equivalent circuit behavior here. Now, because of in the off state, if you can see, there is no interconnect in between. So what we can see is if there is nothing to be connected, they are generally been realized as the capacitance here. So the capacitance which has been here now has been increased, and that's why we are getting a different frequency. The RLC networks remains the same. It is not going to change in any case. However, when you are using some particular on state, there is some diode, so there is an associated resistance which has been used here. So the resistance value changes, and there we are getting a different particular frequency. So the equivalent circuit model remains the same for both the states, whether it is off or on. Certainly, there is a change into the values of C and R, and that's why we are getting two different values of the frequencies as the resonance. So this is how we can realize we can shift the frequency from one particular end to another end just by getting an on and off behavior of a pin diode. Now, another thing is the tunable absorber, where we are generally not looking after for one particular switching frequency, but continuous switching of the frequencies from one to another, and that's why we are using here as a varactor diode, not a pin diode. So a tunable absorber generally exhibits a variation in absorption frequency that can be continuously regulated by the external bias, and the structure has infinite number of states. Now there is not only one state or an off state. You can get infinite number of states, and you can regulate your varactor diode as such that you can get many such particular type of stages, which is going to be depending upon this tunable gesture capacitance, which is dependent on this CJO, which is zero bias junction capacitance. Then another one is VJ, which is potential junction capacitance. This is a grading coefficient M, and then there is a packaging capacitance associated with it. Now, which is the variable value here is just VR. Nothing else is going to change. All other things are remaining constant. And as the CJ decreases, we can see there is a blue shift in the frequency. The frequency increases from 1.25 to 2.75, and they are generally been increased one to another from almost from 0 volt to -1, -5, -8. So if we decrease CJ, we are getting a shift into the frequency, and this is how the tunable absorber could be realized. Okay, so this is one type of reconfigurability that we are getting with the electronic type of arrangement. Now another type of arrangement is the mechanically reconfigurable FS-based absorber. Now you can see here there is some cross dimple type of resonating structure that has been used, and they have been rotated. See, this is the thing. This is the first arrangement when there is no rotation. Now that they've been rotated with some 30 degree, another rotated by 60 degrees. So there is some arrangement made with this particular dumbbell shift resonator, cross dumbbell shift resonator has been rotated, and now we can see with the rotation, we can see that the frequency shifts from 1 to 2, 2 to 3. So this is how the frequency is shifting out with the resonance, because now the incidence angle changes, and because of the changes in the incidence angle, certainly we are obtaining different type of resonant frequencies. Another thing is here what we can see is another type of arrangement. We are using an external electronic actuator to increase the air spacing between this middle air spacing between the bottom FR4 layer and the top FR4 layer. Now what this particular actuator is doing, it is increasing the displacement between these two layers, and because of increasing the displacement, again we are getting a changing into the resonance frequencies. So this is again we are generally obtaining the reconfiguration through mechanically changing the distance between the top and the bottom layer of the absorber. Another thing which has been very important nowadays, the miniaturization of absorber. See, miniaturization is very, very important in order to go for a low packaging type of thing, where we are going to use such type of arrangement such that the absorption characteristics could be obtained, but then the surface current should not be optimally big enough. So what we are getting is we should get some electrically large thing, but the physical size should not get changes. So for that, what we can use, again, we are going to use the lumped elements like capacitors or the vertical interconnects. One type of arrangement is that, and then the very well versed, you all must be knowing about the fractal structures, where we are using the self repetition and increasing the electrical length within the small physical length, and thus trying to increase the frequency. Okay. Now, if we go for the real world application, most of the real world applications are not having flat surfaces. Most of them are cut into nature. If you are going for torpedoes or the firefighter plates, or we are going to use the aircrafts, most of them in particular having the surfaces as the curved surfaces, not the flat surfaces. And the most of the research that has been published into this domain are being the flat surfaces. So it is important to also analyze that we should get some curved conformal type of behavior. So here there are two particular structures where you can see that a PVC substrate has been used or a neoprene rubber substrate has been used here, and they are realized using for the conformal behavior for a difference radius of curvature. You can fold it with some particular degree, and then you can see that the resonance behavior still remains the same. Here we can see the radius of curvature changes from 0 to 90 to 135 to 180, and still the resonance remains the same. There is no changes in the resonances. So such type of thing has also been important to analyze before we go for the real world applications of the FSS based absorber. Now, what most of the things that we have studied till time are the PCB technology based absorbers. We are using the PCB technology photolithography method in order to realize the FSS based absorber. But there are certain limitations of PCB based technology. One is the rigid and the planar geometry. They are generally been very rigid geometry. With a planar geometry, we cannot change the flexibility, we cannot change the conformality. So this is one thing which is one having the limitation. Another thing is the material constraint. We need to be dependent on the commercially available materials into the market. That is the FR4 substrate, PET substrate, Roger. Some of them are FR4 are somewhere for PET or somewhere cost effective. But when you go for Roger or Artiduroid, they are very costly and difficult for us to get it arranged. So this is another particular thing. And then these particular PCBs are not made, they are not optimized for FSS needs. They are generally been optimized for conventional circuitry, and we are certainly using them for our making our antennas or making our FSS based absorbers, which is not the need for which they have been developed or they have been made for. Again, if we are going for photolithography based process, it is a time consuming process for the fabrication of PCB. There are cost implications always associated. PCB fabrication is very costly. As one of the participant, I could hear that there was one question coming from the participant about to Dr. SK Jain, that if there are some particular fabrication facilities available, there are certainly number of fabrication facility available. Although I took care of an idea lab in our institute, which is going to be again a very good type of arrangement given by AICT, having a joint some costing of almost 1 crore rupees, and we do have developed all such facilities in-house. So most of what I am researching on is mostly we are fabricating all our structures in home only at the institute as well. We are not going to get with another, but there are power PCB and another particular such type of vendors are available in most of the cities where you can get such type of thing, but they are very costly as compared to the other type of arrangements which I am going to introduce very shortly to you. Then the resolution is also very low. If the PCB fabrication does not achieve a high resolution required to integrate the FSS designs, and certainly for the higher frequency sites where we are using the millimeter waves. Millimeter waves required a very precise and very small size of top patches as the unit cell size. Now, when we go for a PCB, after a certain amount, we cannot even analyze it from a naked eye. So it is very difficult to fabricate it on this particular type of arrangement. Now, there is an introduction of 3D printed FSS-based absorber very recently in the last 5 years, which certainly represents a paradigm shift, leveraging the manufacturing, additive manufacturing process for advancement of microwave absorbers. I have been using it for most of my research. So what is the benefit of using a 3D printed structures? So enabling the complex 3D structures which allow us for rapid prototyping. We can go with our own design, we can use with our own material. We did not rely on the material available into the market. We can check our own material, and there is a lot of I could say a lot of variety available into the market, as well as they are mostly lightweight and the low cost material. Then if we go for a cost effectiveness, of course, the manufacturing process is very simplified as compared to the PCB technology process, which eliminates the need of expensive tooling and the molds. The process is again rapid prototype based. What we can see, they are fast processing, on-demand fabrication is thing, and generally in 3D printer, if we are putting out some particular thing, we did not supervise it completely again and again, and there is a very low waste that has been associated as we are using the additive manufacturing technique. If we go as compared to the substitute manufacturing, there is a lot of waste which is going out, and it also eliminates the large scale manufacturing process. Their inventory is already available into the market, and we do have wide variety of materials which are already been there, and we can explore it more. So now this benefits position 3D printing as an emerging choice for FS based absorber designs. So if we let me show you the different type of 3D printing schemes which are available with us. So generally, most popular one is the fused filament fabrication technique. So आपने जो maximum देखा होगा, that is mostly on 3D printing that has been available, is the fused filament shape, or the we can say the STM shape type of 3D printing procedure. What we are having is here is we are having a filament that is attached to a spool at the end. Then we do have some rollers, and then there is a nozzle here which generally changes its temperature, and then this filament melt at a certain temperature, and then this particular thing moves from here and there into 3 axes X, Y, and Z, and generally makes the prototype. So this is one type of arrangement. Another thing is wet polymerization, where we are using the UV rays in order to solidify the liquid resin bed here, and then there is a moving platform which moves up and down, and then left to right, and then generally the resin attached to this particular platform, and then the prototype has been developed out here. Another thing is another type of 3D printing technique here is going to be a pneumatic control based technique, where we are using a syringe type of arrangement, and drop by drop the fluid has been coming out, and then it deposits on the platform, and then we are getting the prototype developed. Another type of thing is the powder based fusion technique, where we generally been used for the metallic type of structures to be developed, where we are using the laser material, and then we are using a roller and the metallic powder here, and then this particular the shaft moves from here to here, and this moving bit again moves from up to down, and then what happens, it solidifies the powder at some particular thing, and then what we can do, we can remove the powder at the top, and then the particular shape has been developed, what we can see. Another thing is material jetting type of thing, what we call it as MJ, where a photosensitive resin has been exposed to the UV light, and then they have been jetted with a pressure on a top of a platform, and then it becomes solidified. So they are certainly very famous type of 3D printing techniques. And out of these three, if we compare, the most popular or the most suitable low-cost technique is fused filament type of technique that we are using out. So which is having a low to moderate cost with a resolution of almost 100 microns. Many customized material options are available here. The metallic printing is also available. Multi-material printing is also available, where you can use not only one type of filament, we can use 2 filaments, 3 filaments, or certainly been using 2 different material into one particular thing. So people are even doing research where they are making the layers of one particular dielectric on another dielectric to third dielectric, and then they are finding out their impact onto the design of the absorbers. Then there is no need of post processing in the fused filament method. The thermal stability is also good, and the speed is moderate. So certainly this type of if we compare to all other, they are certainly very costly as compared to the fused filament technique. And other than that, there are very few customized material options available in another. So this is the most popular one. And then if we go for the material, PLA substrate, APS substrate, most of you knowing about it. So they are very popular, and they are into the market nowadays. We can see them into the research. So these are the 3D printed absorbers. So long back in 2018, we can say this is an absorber. These 2 designs has been developed into one lab itself. That is from Sanjung Ling lab from South Korea. This particular thing has been developed. What they can see is there is a truncated cone type of arrangement that has been made. So what we can see that they have just dropped on a PLA substrate, that is a polylactic acid substrate. At the base, they have made some particular type of silver ink as the top mount, And you can see here, there is a truncated shift which generally shifts the frequency from upper to lower side. Now if we go for only a circular patch type of arrangement, this particular frequency must have been somewhere at the higher side. If we want to reduce it, we generally used it for a truncated shift and the frequency get reduced. At the same time, we go for the reduction into the frequency, again the blue shift frequency. What we can see, the same type of concept has been used here by some other researchers. So we can see there is a staircase type of arrangement where we can see a cruciform has been now transformed into a staircase. Now what is the benefit of using such type of arrangement? The benefit is now the electric size has been increased, and even with the same physical size of arrangement, and the frequency shift to the left side. Same concept is again used here, again from the same laboratory. What we can see here is they are getting very good publications out of all these things. They're using a swastik type of arrangement out, swastik symbol they have used, and then they're using some mindering out here at two different levels. So this is the beauty of 3D printing. Now those two different or three different levels are not possible into the PCB type of fabrication. Here we are using at what levels? If you want to increase one more level, this is possible. Although this will increase the thickness, but then the electrical size is so significantly increased that the optimization is much more better than if we are using a PCB type of arrangement. Then if you go for another type of arrangement, to go for an broadband type of responses, in millimeter waves, even this type of responses are there. We are using a honeycomb type of arrangement is here, and then at the top of the honeycomb they are using a square loops type of arrangement. So what they are contributing to now, using this honeycomb certainly gives you a lot of space in between. So they are contributing towards the air spacing. So this air spacing is certainly increasing the bandwidth, and because of this increased bandwidth, we are getting this type of responses. Now this, because of this perforation, again the weight of the prototype and the cost of the prototype certainly significantly reduced, which is not possible in another type of fabrication techniques or the materials which has been used. So these are some of my prototypes that has been there. So what we can see here is I've used very simple type of arrangement that you can see here. We have used two loops, square loops here, but at two different heights. Okay. So what we can see, this is one particular loop, S1 is at one particular height, another loop is another particular height. And because of these two particular heights, what we are getting is we are getting one particular thing that, of course, we are getting a narrowband response because of these shapes, and one particular response at 3.32 gigahertz, another one is at 5.46 gigahertz. But then we do have one particular type of arrangement that can be good here is a binary coded meta surface can be formed, where we can see a 0 1 0 1 type of arrangement. Yes, we do have one level 0 at one level and then 1 at another type particular level. So there is another fabrication flexibility which has been given because of such type of arrangement here. And then what we can see, because of the perforation between this the geometry, we are getting a very good banding, which is not certainly been possible with a 3D printed thing. So if we compared it with the previously published papers, what we can see is for any type of bending material to be used, generally the thickness have to be reduced less than 0.3 mm for the PCB. But here the total thickness is even more than 1.5 mm. Then too we are getting bending. That is only because of the perforation within the 3D printed thing, and we are getting a very good response out of it. So this is the fabricated prototype, and this has been tested out here at IIT Indore, and we are getting the very good responses as compared to the 0-degree responses. Then another degree of freedom that we have introduced here is introducing a 6-fold geometry than the 4-fold geometry. Now, what is the use of having a 6-fold geometry out of it? So here, what you can see, they are generally we are using a 4-fold geometry where the unit cells is certainly been similar at all the 4 folds. But when we are using a 6-fold geometry, generally we are using this hexagonal type of unit cell here, where the master slave boundary condition, if we see here, there have been 6 such particular combinations of master slave boundary, and such type of thing increases the polarization insensitivity, which is less as compared, which is significantly less as compared to this thing into a square shape. So if a square shape is giving somewhere or 30 degree of or 45 degree of the polarization insensitivity, this can be increased to 60 degree or 70 degree using such type of hexagonal type of arrangement into FSS based absorbers. So this has been fabricated, and that we can see that we are getting a very good response here, and even the response has been the bandwidth has been enhanced by bringing the resonances so close enough that we are getting a broadband response as compared to the other particular absorbers. Now another thing is I'm using here is a Lego based concept. So even this concept, when it comes to me, it comes from my 7 years old kid. So when he was playing with this Lego, I could find that it can be a very good substitute for changing the mechanical reconfigurability by just changing the top mount and keeping the base substrate at the same. So what we can see here is, so this is the type of arrangement generally been used. So there are some states which has been elevated on the base. So generally we can see this has been a base ground, and on this base ground what we do have, we do have four types of different resonating tops on the thing, and then on the tops we are having some copper tapes. So this is the full arrangement. There is a copper tape at the bottom, then we do have a base board, then we do have some top mount which can be replaced from this to this, this to this to this. Changing this top mount, what gives you, there is a change in the top mount, so certainly change into the equivalent circuit, and certainly will change into the frequencies. So we are getting one frequency changed from this to this, this to this, this to this, just by changing the top mounts, which is going to be a very good reconfigurable technique without having any complexity introduced, having some active material to be introduced, some lumped elements to be introduced, or some type of very complex mechanical technique to be introduced. Just by changing one particular top mount, we will change the frequency from one to another. So we can see that the absorptivity for the first case, we can see it is going to be 98.92. For the second one, it is going to be 96.5. 99.33 and 99.5, which is significantly good as compared to any other particular type of absorber. So this has been realized, and then we have calculated it. So what we can see that for the measured part, we are getting almost up to 30 degree. We are getting a very good response with the polarization angles for such type of arrangements. Now this particular Lego type of arrangement is coming with a promising technology. So the way we can say that there is another particular thing that we have done it with. So there is an potential to introduce one more thing, that what we have done is we are changing the height of the top mounts and now changing out the frequencies. Just not changing the top mounts, but now changing the heights of the top mounts and then changing out the frequency. The shape is remaining the same. So what we can see here, for this from stage 1 to stage 3, we are changing it. We are changing the heights. We can see that the height has been increased significantly from here to here, here to here, and also the top copper tape that we have used, that has been elongated now. For the first one, it is only on the top. For the second one, we have even on the side faces we have elongated it. For the third one, it is again elongated, and thus the electrical size has been increased so far. And what we can see, we are getting the similar thing we have introduced with three structures. One is the small cruciform, the large cruciform, and there is a swastik shape. What we can see here is we are getting a very good miniaturization achieved. From stage 1 to stage 3, we can see miniaturization that is achieved is 53%. From stage for the second two, we are getting almost to 36%, and for the third structure, we are getting it for 20.4%. So a good significant reduction into the size has been introduced. The resonant frequency changes from 4.89 significantly to 2.66 just by changing the top mount, the height of the top mount. So this is one more thing that we have introduced. This is how the 3D printing brings a lot many advantages towards the FSS fabrication, and there are certain such very good designs already available. With people are doing a lot of work with the curvatures, the conformability nowadays using 3D printing techniques. So I hope this is all from my side. These are the references, and thank you so much to Ranjan Bala Madam, BS Institute, and the team. I hope I am on time.
Yes, sir. Yes, sir. Thank you so much, sir, for enlightening session and analytical expertise. Sir, there is some question.
Yeah.
From Frida Madam. Will dielectric with metal backing be called meta surfaces or frequency selective surfaces?
So there are many certain particular questions that are coming to me many times, that what is the difference between meta surfaces or the meta material and the frequency selective surfaces. So I'm giving a very clear cut answer to this. So when we talk about meta surfaces, we can call them as a subset of frequency selective surfaces. In meta surfaces, generally there is a limitation that the size of the unit cell should be very very small as compared to the size of the wavelength. However, in FSS based thing, we are not limited with the size. In FSS, we can even go with a lambda, 2 lambda, 3 lambda type of unit cell provisions. So, of course, all metamaterials are or meta surfaces are frequency selective surfaces, but not all frequency selective surfaces are meta surfaces. I hope I've answered it.
Okay, sir. Any other question from the participants?
Yes, sir. Gaurav, sir?
Yes, sir. Yes.
Yes, sir. Good evening.
Yeah.
Sir, actually, nowadays, most of the people are discussing about IRS,
Yes.
which is nothing but a special form of, I think, FSS or meta surface. So there they are quoting that they are changing they are doing beam forming or other thing they are doing with the help of that reconfigurable reflecting surfaces. And they are doing those things by FPGA. So anywhere in India they are doing this, or still that IRS is in the research paper only.
No. IRS has been very extensively been researched nowadays by people. So I can give you certain very good references. People in see, you must have heard Dr. Saptarishi Ghosh yesterday. So
Yes, sir. Yes, sir.
in his laboratory there is a very good work going on IRS. Another particular very good center for IRS people are doing very good work is IIT Kanpur, where Dr. K.V. Srivastava sir's laboratory people are doing very good work on IRS. Even at IIT Kharagpur also they are doing it. So what is IRS? Certainly, they are getting some intelligence in the reflective surfaces. And how to make a reflector, I've already taught you today. How to see, absorber is just an reverse to the absorber is a reflector, isn't it? So we are just making it out and giving them some intelligence that is through using giving some particular type of arrangements that they can reconfigure, or they can certainly change the frequency of their own. That is the thing. There is nothing very dynamic going on, although there is a lot many things going on in the communication side. But if we say for in the terms of fabrication or the structure type of thing, there is very good work which is going on, and you can refer to that literature.
Okay, sir. Thank you. One more thing, sir. In terahertz domain, also people are discussing, but in terahertz domain, fabrication facility is not available in India.
No, it is
So,
there.
suppose,
IIT Kanpur is doing this. IIT Kharagpur is also doing it. So you can always connect to. I think Dr. K.V. Srivastava's lab is doing it in on terahertz frequency as well, and they are coming up with very good. Even I could say triple ITDM Jabalpur. It is also doing very good work on terahertz frequencies. So
fabrication is going on, sir, because I have a doubt that fabrication.
They are getting some particular fabrication facilities for sure. They are not taking, because I have read some paper where they have used some in-house fabrication techniques.
Because in terahertz, the antenna will be in the micrometer range. So how they are doing and what connector they are using?
Micro machining, they have been using it for. IIT Kanpur, it's for sure. You may just connect them once.
Okay, sir. Okay, sir. Thank you. Thank you, sir.
Yeah.
Any other questions from the participants? If not, we can proceed for the photo. I request everyone to please switch on your camera for 2 minutes. Photo team, Anuradha madam, is it done?
Yes, madam, I'm waiting because lots of people have not turned on their cameras.
Okay, fine.
Yeah, all the participants, please turn on your camera for 2 minutes only.
Thank you, everybody. It is done.
Thank you
Thank
so
you, thank
much.
you, sir. Thank you so much, sir. It was a pleasure connecting with you, sir. Thank
Same
you.
here, same here.
Thank you, Sir Gaurav, sir. Thank you very much.
Thank you, ma'am. Am I allowed to leave now?
Yes, sir. Yes.
Yes, sir. Yes, sir.
Thank you, Ranjana Bala madam. It's a pleasure seeing you
Thank
after
you,
a very
Gaurav
long
sir.
time.
Thank you, Dr. Gaurav.
All the participants, please fill the feedback form. The link is
Yes,
already
link is
pasted
there.
in the chat box.
We'll wait for 5 minutes, no? 5 to 10 minutes, Monali madam.
Yes, yes. Rasika, if you want, you can leave.
Okay. So we
Yes,
are
yes. Please.
concluding our session and to once again very happy Makar Sankranti. Good night all.
Same to you, ma'am. Same to you and all.
Good night all. See you tomorrow.
Yeah, good night. Thank you, Dr. Rasika.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, everyone.
All the participants, please fill the feedback form.
All the participants are requested to fill the feedback form and leave the session.
Yeah, Ranjanbala madam, should we wind up now?
Yes, I think we can.
Ha.
All the participants are requested to fill the feedback form and leave. Sorry, Arul sir. Uh, thank you, participants. Good night. See you tomorrow.
Can I close Meet?
Yes, Anuradha.
मैम एक मिनट आई थिंक
People are filling the feedback form. Yes, just wait.
Okay. We'll wait.
3 more minutes we can wait.
Yes.
Can I leave, ma'am?
Yes, Rasika.
Yes, Rasika, you can leave. Thank you.
Okay, thank you, ma'am.
नाइन्टी सेवन हुए हैं मैम अराउंड अभी तक.
Okay. Participants, please fill up the feedback form.
Can I stop recording?
हाँ मैम रिकॉर्डिंग स्टॉप कर सकते हैं.
Yes.
हाँ अनुराधा.
मैडम लिंक